block a lot bigger and actually made their local routing more flexible, and they said they did that for increasing wire resistance as well. So it's a major driver now of how people are altering their architectures. Okay, so we were kind of going through a few final principles of routing architecture. So I said that, we've said that found a few times that it's actually a bad idea to have hard boundaries. So hierarchical FPGAs have these kind of hard boundaries where you cross a certain point, and even if you're physically close together, you have to go through another level of the routing hierarchy, and your delay goes up a lot. So that's part of why we said it's better to stagger the start points of these wires. But it seems like we still have kind of a hard boundary. To go between these two red, to go between these two red blocks, we use a single routing wire, length 4. To go between this red block and blue block, we'd still use a length 4. So even though we got physically closer, we didn't get much faster, because mostly the delay of that wire will be set by how much capacitance the driver has to discharge. So we could do a bit better. We could add in some length 2 wires, and most architectures do that. They have a range of wire lengths, so they would have another option. So that's one thing you do. You have multiple types of wire. But fundamentally, once we get this far away, we're right beside a block. We can't do any better, even if we have some really short wires. We kind of hit a lower bound. So if you look at what happens, we have to go out through a routing driver across a wire. Could be length 4, could be a bit shorter. And then we have to go through some muxing and some local interconnect to get back in. So there's kind of a lower bound on how fast we can get between this block and this block, even though they're right beside each other. So could we do better? Whoops. Okay, so, and the answer is you can. So basically, we've kind of created a hard boundary with our logic blocks. They have a routing hierarchy inside of them. We've got a lot of advantages from that, but it does mean there's kind of a lower bound on how fast we can go between these, because we have to go out, go to the regular routing, go back in. So, could we do better? And you can do better. So a lot of FPGAs they use different terms. Sometimes they'll call them sneak paths, sometimes they'll call them direct connect, but basically some faster path to immediately adjacent logic blocks or DSP blocks, etc., like whatever's right beside you. Because in theory, you could get there faster. You're physically very close. Maybe you don't have to go to the regular routing at all. So this is an academic study. So there's a paper by Rupchand Singh and Rose that looked at, is it a good idea to add these direct connections between logic clusters that kind of can skip some of the routing hierarchy? They don't have to go out to the general routing, back in through my local routing. Maybe they can just skip some of that delay. So what they did is they said, okay, my normal routing path is, I got a basic logic element, so LUT and flip-flop, and it has some buffer, because it's going to drive a fair amount of capacitance. Then it goes to an even bigger buffer. So the electrical design of this matters, because they're trying to figure out, can they make it faster? So they say, okay, I got a little buffer, then I go to a big buffer, and this big buffer can drive various pass gates. So they're using a tri-state buffer style of architecture. It's not one of those directional ones that we looked at last week. And that drives, routing wires that span several logic blocks. And then from one of those routing wires, well, you have multiplexers. This is your input switch block that's listening to some of them. So we can go through this input switch block and into this logic block. And then it's not shown here, but inside this logic block, there'll be some local interconnect as well. So there's a reasonable amount of delay to get between these things. Go through a couple buffers, a routing switch, drive a fairly large capacitance that is a routing wire spanning multiple blocks, go through another multiplexer, and then actually go through some more muxes inside here for the local interconnect, if I want to get to a lookup table or a BLE over here. So they looked at, well, could we do better than that? And they said, yeah, what we could do is we're actually going to make another buffer, okay? And the reason we're going to make this other buffer is we want it to be fast. We want it to be relatively lightly loaded. So we're actually going to split the signal path, the output. It's going to go through a smaller buffer goes straight across to this routing mux and into the local interconnect. So we cut out this routing driver, we cut out the capacitance of this routing wire, and we went straight into the local interconnect, well, the mux that gets us to the local interconnect of the block next to us, so into its connection block. Okay, so, and they found that this did indeed work. They got a gain. So in their study, they looked at various options of how many of these sneak paths should they have. If they had, a moderate number, like not too many, it was faster. They were able to reduce the delay of the average circuit by 6%. Some circuits didn't really benefit much because their critical paths didn't have a lot of these, very short hops. Some benefited more. It cost them some area. So it made the chip about 4% bigger, but it did reduce delay, so they concluded it was a good idea. The other thing this does is it helps hand optimization. Like this puts a higher upper bound on your performance. So if you're willing to go in and really fine tune your design, you can get somewhat more probably than they found because you're willing to change the design and try to use these even more. This is basically what could they get automatically from the CAD tools without you retuning your design. So there's sometimes a bit of an advantage too to just increasing the performance ceiling of the chip so that people who really want to optimize have some more room. So they found modest gains, but there were gains. And that's pretty indicative of what I saw in industry as well. There were gains from these kinds of connections. They're not huge, but they are real. So most commercial FPGAs have them. So in Altera Intel, they usually call them sneak paths. And what they do is that one cluster, so a cluster could be a logic block, but it could be a DSP block, could be a RAM block. They do it for all of them. Can basically drive the local interconnect of the block to its right. And you can also drive the local interconnect of the block to your left. Right? Actually, maybe it's better to draw it this way. So this block can drive that one, this block can drive, and it can also drive that one. So you've got two nearest neighbors that you can connect to with extra fast paths. Xilinx is does something similar, but they have more direct connect. So they don't just draw, the one to your left and right. They actually have 8, all the diagonally adjacent blocks. So, so this costs a little more to have more direct connect, but it gives more opportunity to get speed. So that might be one reason they do this. Maybe they chose different speed versus area trade-offs. But there's another reason. Did anybody think of, this might be unanswerable, because I can't remember if I mentioned this or not. Can you think of why Altera does this and Xilinx does this? Because there's another kind of fundamental reason why each of them does something different and they'll probably never change. Like this is a case where they'll probably never copy each other. Yeah? Let's see, that is true. Yeah, for Altera devices, they do lay things out where they make their logic blocks usually taller than they are wide. They're usually on the order of 1.5 or 2 times as tall as they are wide, and they make their horizontal channels wider than their vertical channels. So that is true, and you're right, that does actually make direct connect in the horizontal direction a bit more desirable. There's a kind of a fundamental reason though why does Altera tend to make their logic blocks taller than they are wide, and their horizontal channels wider than the vertical ones. Any idea? So this might be an unanswerable one if I haven't told you this. So Altera is one of the, this is now happening with some other chips like Cerebrus, the wafer scale engine. But it was one of the earliest companies that made logic chips that were repairable. Okay, and there are some other ones now, like as I said, Cerebrus, where they have this huge array of processors. So memory chips for a long time have been repairable. You buy a DRAM chip, and you buy a 4 gigabit DRAM chip. If you actually were to crack it open, count all the bits, which would take you a long time, you're probably going to find that it's actually about 4.1 or 4.2 gigabits. But you can't use it as a 4.2 gigabit DRAM. The reason is DRAM's really regular. Okay, so it's actually built out a bunch of subarrays of memories, but each of those subarrays has got a bunch of rows and a bunch of columns. And if they need 128 rows per subarray to get to their density, they won't really build 128. They'll build like 129 or 130. They build more, okay? At test time of the memory, they check which bits are bad, or which rows are bad more specifically. They don't really care which bits, but for some reason this row is bad. If that row is bad, they program some fuses inside the chip, so non-volatile fuses. So this is all done at manufacturing test time. And that basically deactivates those rows. And instead you access the other 128 rows. So as long as, in my example, of no more than 2 rows were broken in any of these subarrays, it's okay, right? You can have defects in the chip, but you'd still be able to sell it. Okay, memories have done that for a long time. So SRAM, DRAM, processor caches, the bigger caches will also have this. They'll make the cache a bit bigger than it has to be, and they'll test the rows and the fuses to turn off the ones that are broken. It's harder to do with logic. Memory's really regular, but an FPGA is more regular than most logic chips. So what Altera does is this is in all of their larger FPGAs. It's not done in the smallest FPGAs, because the smallest FPGAs, you're less likely to have a defect. But in their larger FPGAs, so the Stratix series, if you buy a chip and it's supposed to have 100 rows of logic, it's really got about 104, okay? You can't use all 104. At manufacturing test time, Altera determines are there flaws in any of these rows. If there are flaws in them, they program some fuses in the chip to say these are broken rows, and they steer around them. When you program the chip, the programming hardware is actually smart enough to read those fuses and actually skip programming those rows and instead program one of your 4 spare rows. Does that make sense? Okay, this is actually pretty tricky to do because it has to be hidden from the end user. So, okay, so I've got a row. Let's see, I've got some connections, say, going from here to here. So that's a connection. I'm making it with a wire. So I've got some logic here. I've got some logic here in that connection. And maybe I've also got, say, let's call that L1 and L1. And maybe I've got another connection. L2 goes up to this L2. Okay, so I've got another connection that goes like this. Okay, so let's say that's my whole design. Okay, my whole design is like these. Well, let's say it's a piece of my design, but it's representative. Maybe that's more realistic. So I've got some vertical routes, some horizontal routes. I've got some things used. Let's say when this is tested, and let's say in my FPGA, I built 1 extra row. Okay, so this is never, the CAD tool will not show this to me. The CAD tool tells me this is a chip with 2 blocks, not 3. If there's a flaw, and let's say this row, something's wrong with it. It might be the routing, it might be the logic. Let's say there's a problem with this logic block. Okay, there's a defect in it, something doesn't. FPGAs come fully tested, so they program all sorts of designs in it. They'll detect there's a problem with this logic block. And what Xilinx would do is throw the chip away. Okay, that's a normal technique. Didn't work, it's got to be thrown away, make another one. So obviously that makes things more costly. What Intel does is they detect this as broken and they'll mark this row as wrong. Okay, so there's a fuse here. So it's a non-volatile element that they can program once and it'll remember. So they program this essentially with a 0. This one passed, so it's programmed with a 1. This one passed, programmed with a 1. And now when you buy this chip, instead of programming this row, the programming hardware will move all this down 1. Okay, so all of this will in fact go here. L2 goes here. This and this, it puts a significant constraint on your routing though. The horizontal routing, I actually didn't show a horizontal route. Let's put another one here. Let's say there's a horizontal route from here to here. Okay, if I want to shift this down, I program L2 in here. Let's say this is another one, L3. I program L3 in here. So that's fine. I just program those logic blocks instead of these ones. I program the routing. So I program this wire instead of that. Instead of this wire, I program this one, and I make my horizontal connection. That's all good. But I actually need this vertical connection to work too. And this is actually quite tricky. So the way this works is all the wires in an Intel FPGA are 1 unit longer than you think they are. So if the data sheet says, for example, there's a C4 wire, like a vertical length 4 wire, it's physically actually five units of wire. It spans 1 extra logic block. And the reason is in case they have to shift a whole row down. they can still reach this wire because that wire is actually longer than they told you. And all of the switch patterns, et cetera, have to be designed so that this works. So that when you shift it down, you're still connecting to the right wire, everything gets connected properly. Everybody with me? Okay, so what this means is that vertical wiring is more expensive, okay? Because every wire is actually 1 unit longer than you think. Also means that the vertical wiring, it's harder, you need some tri-states basically, or some real cleverness, okay? So, but basically the vertical wiring, even if I said there's a single drive point in my architecture, that's the only place I can drive something, I actually really need 2 drive points, because I might shift the whole thing down by 1. So I need to put a tri-state buffer on that. Instead of just say there's 1 buffer I can't shut off, that's actually not gonna work. I gotta move the buffer down here. Does that make sense? Now actually Intel has some clever techniques where sometimes they can get rid of the tri-state, but all of it makes vertical wiring more expensive than you think. And it means it's particularly more expensive for short vertical wires. If you have a length 4 vertical wire and you merely make it 5 and you hook all the switches up for 5 blocks instead of 4, okay, it's kind of 25% more expensive than you thought. If you have a length 1 vertical wire, it actually turns into length 2. Basically costs double what you thought. If you have direct connects in an Altera architecture that go up 1, they can't really go up 1, they actually have to go up 2. So they're basically twice as expensive as you think, and not as fast as you think. Does that make sense? So they just don't build them. They really don't want to build short vertical wires because this addition of repairability is going to make those short vertical wires more expensive than you'd like. It makes them undesirable. So that's why they don't do it. Xilinx doesn't have repairable chips. They don't do this, so they don't care. So they make these direct connects vertically as well as horizontally, and it's logical for them. Does that make sense? So Intel's, for many years, this was kept very secret within Altera. Like people at Altera knew it, but it was something that Altera never talked about outside because it increased the yield so much. And it was very tricky to do. So my group at, when we were acquired by Altera, my group made the Stratix architecture, and we did not want to make this work, actually, because we were like, this is too complicated. For hierarchical FPGAs, the older Altera FPGAs was much easier, right? Because you had a hierarchy that had 12 rows. If you just made it 13, it was pretty easy to see how that worked. It was much harder with this irregular routing, and we wouldn't have actually made it work except the person in charge of manufacturing at Altera, the chief operating officer, was very powerful and said, you will make it work. And it's actually interesting because it was good we made it work. It was, but it was one of those cases where like actually you needed a top-down management directive of, I don't really care about any details or any like whining or whatever, like you're just gonna make it work. So anyway, but that's like one of the things that has led to some fundamental differences that will probably never completely converge between Intel and AMD, unless AMD decides to make their chips repairable too. Let's see. Actually, I'll ask one more question. So I said this was hidden to the end user. There are some academics who have basically said, hey, maybe we could just mark what parts of the chip are broken, like specific wires, specific logic blocks, specific DSP blocks, and every single person who buys a chip will just have them rerun the CAD tools. So, and that way they could use broken chips. So what do you think? Good idea? So Amin's shaking his head. He writes CAD tools. He's like, I don't want people writing my tools on every chip. Anybody else like it or not like it? So you kind of like it? Academics really like it. There's a big problem with it in practice. The big problem with it in practice is the money in FPGAs comes from production runs, not from like prototypes where you're just going to like make one prototype. It's where you're making thousands, hundreds of thousands of boards with these chips on them. Those companies are basically putting these boards on, programming the FPGA, testing it. They do not have somebody sitting there running the CAD tools and saying, I have a timing violation, right? Which happens. The CAD tools aren't perfect, so you run the CAD tools again with a slightly different map of what's broken and what's not, and they may say, I didn't close timing. Also, they don't say, companies don't say, okay, you said that the design closed timing, meaning there are no timing violations, it runs at this frequency, therefore it's all good, I'm going to ship it. It's probably good, but they're still going to test the board. They're going to test the board in case there's a problem. What if there was a bug in the CAD tool? What if their timing constraints weren't quite right? So they don't trust it. So it means that the notion of like you're going to rerun the CAD tools and fix any problems for every broken chip is not feasible. But that's not what Intel does. It's invisible to you, right? The programming hardware just adjusts your bit stream, basically. As the programming goes in, it just shifts things around. The other thing they do that's really important is the timing doesn't change. Okay, so when I repaired this, so this row's gone, okay, and it all got shifted down by 1. So you can say, well, wait a sec, didn't that slow this down? Like you told me it was a wire that was 2 units long, and now it's 3 units long. So what do you think? Did it slow it down? Yeah.
You said that the delay primarily depends on the capacitance of the wire?
Yeah.
So it should.
It does primarily depend on the capacitance. There's some resistance. So it did probably slow down a little bit, but probably not that much for such a small change. But the other thing is that it did slow down noticeably compared to if I had made a chip that just had two rows. Like this vertical wire only spanned 2 rows. Basically, Intel's timing models take that into consideration. So they know all the wires are longer. They know the worst case is that you're going to be 1 unit further along the wire than you would be. So they actually always timing analyze that way. So they just add conservatism to the model. So there's a price that they pay. When we did this for some of the Stratix chips, we did pay about 4% delay penalty, and adding in the extra switches that we need and tri-states and the extra rows is another maybe 4 or 5% area. So it's not free, but the cost is not exorbitant. That more than pays for itself if you have big chips where you could have a pretty high chance of a defect. It doesn't pay for itself for small chips. And so for the smallest chips, they don't do it. Like the Cyclone series family doesn't do it. The Stratix series families do. Does that make sense? But that's another important part of it, is like everybody pays the timing penalty, whether or not they're skipping a broken row. And that guarantees that they don't have to retiming analyze their design for all sorts of possible cases, which they're never going to do. Right? Like that would not be feasible. Does that make sense? It's kind of a long digression, but it's actually pretty interesting how these chips are made repairable. So, okay, so that was a little bit about local interconnect. And I think I see somebody in the chat. Let's see. Okay, that's you, Amin. That sounds good. Okay, a few last routing ideas, then we'll move on to the next thing. So speed unbalanced routing. So this is an optimization you can do in a few different ways. You want to make the critical path fast, and you want to make, but your speed of your design is limited by not everything, just the longest paths. So if you can make those longest paths fast, that's good enough. You could make other paths could use slower resources, like slower wiring that might not cost as much area. So this is actually a result from myself way back in 1999 in my PhD thesis. And basically, these are runs from VPR where I was changing what fraction of the wires were spaced out more. So I had a certain amount of room to put wires over top of my logic blocks. I could put them all, pack them all as tightly as I could, and that'll fit the wiring in densely. But they have a bit more capacitance, they're a bit slower. Or I could space them all out, which makes things faster by about 15%. And that's fine as long as you have enough room, but sometimes you don't have enough room to space them all out. It might not fit over top of your logic block, and you probably really don't want to make that bigger. It's going to get expensive. So, what happens if you space out just some of them? And the CAD, because the CAD tools are timing driven, they're actually constantly, well, not constantly, but often performing timing analysis with the current delays of your circuit implementation and deciding where are the critical paths and trying to make those faster. They don't actually need all the wires to be fast. So in this study, if about 20% of the wiring was fast, it was almost as good as 100% of it being fast. So you get this kind of 80-20 rule. This is from Stratix 2, okay? And in Stratix 2, the same trick was used, but in a different way. So this is basically a routing driver. So you've seen this before. This is the inverter. This is the weak keeper. This is actually another inverter. So this is another inverter because we want to have a buffer instead of something inverting. And we make this one actually extra big because it's going to drive a bunch of load. And what you have here is actually a 2-level pass transistor mux. So it's basically what we drew on the board. These are SRAM cells controlling it. So let's see if I can show you the whole thing here. This is one level of the mux, and this is the other level. So that would be, these three inputs get selected, and then you pick one of those. Or these three inputs, you select one of these, and then you pick one of those. Okay, so and these are all routing wires. So that's a routing wire, routing wire, routing wire, routing wire. So this is a routing mux. There's a whole bunch of routing wires coming in. And basically, almost all the paths go through 2 pass transistors to make it through the mux, because that's the most efficient way we found to make a routing mux. But what Altera did in this chip is they made a few inputs go straight into the second level of the mux. Okay, so this fast input doesn't go through 1 pass transistor, 2 pass transistors. It just goes through 1 pass transistor. So it's faster. If we did this too much, we'd get essentially we'd degrade back to a 1-level mux, which costs a lot more area. So remember, we analyzed that, and we need more SRAM. It costs more area. But they don't do it for everything. They just did it for a couple of inputs. So 1 or 2 inputs went straight into the second level. And they found that the CAD tools were, again, pretty good at taking whatever's on the critical path and putting them into those fast inputs. So they got about 4 to 5% more speed just by making 1 fast input per routing mux, and it didn't cost them very much area. So this was much cheaper than making all the routing muxes just 1 level, which would be a lot bigger. They got most of the gain. But yeah, if they keep doing this, they essentially are starting to degrade back to a 1-level routing mux, which isn't a great idea for area. I guess a question I'll ask you is, could I combine these 2 ideas? So I said, well, we could space out some wires. Now Altera's got this idea of maybe I can take some wires and put them into just a faster input in my routing muxes. What do you think? Do you think you can combine these? This is one of those questions where there's no wrong answer, right? The answer is kind of. So what do you think? How would you combine them, right? So let's say you tried to combine them. What would you do? What do you think? Well, okay, so I could make some wires fast with spacing, and different wires go into this fast input. Or I could pick 20% of my wires and make them extra fast with spacing, and also make those same wires go into the fast input of my routing muxes. So those are 2 different ways I could combine them. Kind of don't overlap them, or pick you're the chosen golden wires. You're both spaced out and you're put into the fast input. So what would you do? Would you kind of say, no, let's take 2 different groups of 20%, or should we make 1 group of 20% that gets both optimizations? You said make 1 group? Yeah, so 1 group makes more sense. Try to stack them. If you, otherwise, the CAD tool's it can never get the best of both worlds. Your absolute fastest option just doesn't exist. So you probably do want to be careful and say, I'll make these wires extra fast using each technique. Eventually, this does start running out of gas. If you make them way faster than everything else, then you'll probably have some other paths that start becoming critical. So but that usually you can't make them that much faster. So you can combine these techniques. Eventually, if you make stuff fast enough, some other stuff starts becoming critical. So you can't take this, just make 20% of the stuff extra fast as kind of an absolute. No matter how fast you make them, and no matter how many limitations you put on them, it's always okay. Eventually, you'll get some declining returns. But you can combine them somewhat. Okay, so I think this is the last idea I have on routing. Bus-based routing. So the idea, this comes up a lot, right? Academics have looked at this, and actually it drives a bunch of industrial, actually it's mostly academic things. So a bunch of different academic efforts have kind of looked at this and continue to look at this. So the idea is most of a design is computing on multi-bit quantities, moving around multi-bit quantities. So if you think of the designs you did in lab 1 and lab 2, most of your logic was actually not in the control, where it was 1 bit in a state machine. Most of it was actually 32-bit adders, 16-bit adders, 16-bit registers, 32-bit multipliers, etc. So it was buses, and that's pretty common. And then, the number 1 market for FPGAs is communications. In some communications where you're processing a lot of high-speed data, the buses get even wider, because you've got to go really parallel to move all that data, with the throughput you need. But despite the fact that most of our logic is in buses, FPGAs actually have the flexibility to do computation bit by bit, well, at least a lot of the computation. So our lookup tables can do a different thing for every bit of a computation, and our routing, every decision in routing is like 1 bit wide. We connect this wire to that wire or we don't. Okay, that's like a 1-bit decision. Does that make sense? We can route every bit of a 32-bit bus in a completely different way. So maybe that's overly flexible. We don't really need to do that. We could just route around entire buses and we could save some area. So the savings would be SRAM bits, right? Right now we have every routing switch has SRAM bits choosing what the path through it is. And if we said we were going to do entire buses, we wouldn't need SRAM bits for every routing switch. We could share them. Does that make sense? Like a whole bus could share them and make all the same decisions. Okay. The cost of this is that we might waste wires and switches. Okay, for a few reasons. Like in my architecture, if I say I'm going to make all the routing 32 bits wide, meaning I've got one set of SRAM cells and they always control 32 switches. So that all 32 bits of a bus must move around together. What if I have some control logic that's only 1 bit wide? I'm going to waste most of that bus. What if I have some 8-bit buses? What if I have some 40-bit buses? I'm going to get some wastage due to the buses in the design not all matching what I chose to put in the architecture. Does that make sense? So that's the basic reason. So there have been a few different efforts that have looked at this. This is one by Yi and Rose. So they kept the logic blocks the same, but they say here they take 4 conventional logic blocks. Okay, so they can compute 4 bits of data. And those 4 bits of data come out of the logic block and they move in lockstep. Okay, so one set of SRAM cells will control their output connection block. So all 4 of these wires, for example, would connect to all 4 of these outputs would connect to these 4 wires. Okay, so the first one connects to this wire, second one connects to that wire, third to that, fourth to that. They have maybe an alternative choice of they could alternatively connect those 4 outputs to these 4 wires. But again, if they choose to do that, the first bit will connect to the first wire, the second bit to the second, and so on. Okay, so they still have flexibility, but it's not a flexibility where they can choose for every output where does it go. Groups of 4 outputs now you get connected to these 4 wires or you don't. Or maybe you get connected to these 4 wires. In the switch block, it's the same idea. They put all the switches in. This is like the switch pattern you get with an FS equals 3 switch block. So they still put all the same switches in that you would usually put in, but they control them with one set of SRAM. Okay, so, and then the same thing on the input connection blocks. So let me just draw what happens. So let's say I needed to get these signals, the outputs from this block, back to the input. I might choose to use this group of wires. So I'd program in one SRAM setting that makes all 4 of these outputs connect to them. I need to go left. I'll program one SRAM cell to say everybody's going to get connected to the wire going left, because that SRAM cell is going to control 4 different switches. Okay, so I only need one SRAM cell. And then I'd program another setting that's shared across these 4 muxes to say you're all going to listen to that group of 4 wires. Does that make sense? So these 4 bits now kind of get routed in lockstep. And my savings was SRAM cells. So what do you think? Is this going to be, it's going to save me a lot, it's going to work well or not? What do you think? It depends. So it's always a good answer. So you're ready for academia, right? So if you can always, you'll never be lost if you can always give one of those answers that can be taken either way. So it's good. I commend you. So what does it depend on? Okay, so you mean, what do you mean by that?
For example, how many these you need to use as an input and output?
Yeah, okay, so you're saying if it doesn't divide by 4 very well, it's not good. So if it was all a bunch of, I don't know, bit twiddling or control logic where it's all 1 bit, this is wasteful. That's true, so that's a problem with it. If I had a lot of 7-bit buses, it's okay. I guess I'll round them up to 8 so I can do that, but I'll waste a bit. And that's actually why they did 4-bit buses rather than 32 bits, because the wastage with a 4-bit bus is not so bad. If you have a 7-bit or a 15-bit or a 16-bit, if you decide you're going to do 32 bits and then most of your data is 8-bit, it's pretty bad, right? You're wasting 3/4 of your wires all the time. So they chose a relatively narrow bus. Yeah, so that's one inefficiency that you get. Anything else? I guess the other thing to realize is that you're only saving SRAM cells. When people look at this at first, including myself, you think, well, you could save a lot because we spend so much area on routing. If we route buses, that should be a lot more efficient. The problem is they still have all the switches. They can't get rid of the muxes. They can only share the SRAM cells. And that's not trivial. A typical FPGA spends about 25% of its area on the SRAM cells that control the configuration. So a lot of your routing area is at the SRAM cells. But a lot of it is also the routing switches. There's even more in the routing switches. So your gains are kind of capped by the fact that there's only 25% of the areas going into these SRAM cells that you're trying to share. Okay? So what they found actually is they did get gains. They got about 10% area reduction. They didn't get any speed enhancement, which makes sense. There's nothing in here that should be faster. But they got about 10% area reduction on designs that had buses. It doesn't make sense to try this architecture if it's all 1-bit, so they didn't try that. Their best architecture used 4-bit bus widths, and half of the wires were bus-based, and half of the wires were just regular, 1-bit control. Why do you think they did? I guess I already told you why they did 4 bits. They don't want to have too much round off. Why do you think they only made half of the wires bus-based? Because it's also going to kind of cap their gains. But they tried other ones. They decided 50% worked the best. So it wasn't just that they just picked it out of a hat. Why would you leave a lot of 1-bit wide buses or 1-bit wide routing?
Reduce wastage.
Yeah, you use wastage. And you do have misalignment. Like you do have control logic, so you need some 1-bit quantities. You do have buses that don't fit nicely to 4 bits, not divisible by 4. The other thing that you get is even if you're working on, say, 32-bit quantities, let's say I'm adding them together. What often happens is the last bit might be special. The last bit I might have to check for overflow. Okay, so even though when you're writing your HDL, you're writing it as 32-bit quantities, after you've gone through synthesis, those 32 bits aren't all doing the same thing, right? The last one is doing something different. Maybe the first one is doing something different. And that means by the time it gets to the CAD tools, it doesn't actually look like a 32-bit bus that's identical. It might look like the 30 bits are identical, but the top one and the bottom one are different. And it has to be routed differently. So the buses are often a little more irregular than you think when you're just running your HDL by the time you get down to the low-level CAD tools. So those are all issues. So I kind of mentioned all these. And yeah, SRAM, not just in the routing, but just total SRAM is like 25 to 30% of your area. So if they save 10% area by cutting that from 30% to 20%, it's actually not bad. But it's not an enormous area savings. Okay, so people haven't given up on this idea, but it means that it's not enough to get a big gain by itself. The idea is maybe larger gains are possible if we change more stuff. Okay, so just changing some of the routing to be bus-based isn't going to get us a big gain. But what we could do is say, well, lookup tables, which are kind of the dominant part of the FPGA logic fabric, they can do a different thing on every single bit. And maybe that's more than we need. Maybe we don't need that flexibility. So maybe instead of lookup tables, I'm going to make my function blocks, my logic blocks, sorry, this is hard to write on. Let me put this down. Maybe I'm going to make my function blocks be ALUs. So maybe I'll have some lookup tables, but maybe I'll have a lot of my my blocks are actually 16-bit ALUs. So that lets me save some area by making something that's smaller than lookup tables. You can't do everything anymore. Like it does a 16-bit operation. So if you need a whole bunch of like 1-bit operations, it's not good. But if you needed 16-bit ones, it is good. So that's one of the things they do. So they make a coarser function unit like ALUs. They use bus-based routing. which we just saw. And then the last thing you have to do if you want to make this kind of device efficient is the routing switches are still expensive, and they don't get cheaper. Their SRAM gets cheaper, but the switch itself does not get cheaper just because you're switching entire buses. So the last thing to do is they use routing architectures that are quite inflexible, much more inflexible usually than you would use in an FPGA. So I'm showing here, and if you do all these things, this is usually called a coarse-grained reconfigurable array. So it's kind of like an FPGA, but it's made these changes. Well, it's a lot like an FPGA, but it's made these changes. And the thing you'll notice about coarse-grained reconfigurable architectures is they tend to have things like nearest neighbor connections. Like that's what I'm showing here. Like this, these ALUs, or function blocks that I've shown, they can only connect to their nearest neighbors. And in an FPGA, you probably wouldn't do this. People did it early on, but it's really hard to route, so people don't like it. In a CGRA, there's more pressure to do this, because once you've made these changes, you've made your function blocks smaller, you've gotten rid of a bunch of SRAM controlling it, you kind of would really like to get rid of routing switches. It does make it difficult, though, for the CAD tools to map designs to it. So it's an active area of research. The jury's a little bit out on it still, of can you make this work well or not. In theory, you could make it more efficient for these data path operations than an FPGA, but in practice, it's been somewhat difficult. Yeah?
What sort of applications are CGRAs better than FPGAs?
So mostly that people think like compute applications. Okay, so if you think of, let's say DSP processing. So you're doing DSP processing, you're doing a lot of multiply accumulate, maybe on 16-bit data, which is usually used in like wireless filtering and so on. So we're building 16-bit data, but using 1-bit wide routing. We're using lookup tables plus adders for some of the arithmetic, when maybe an ALU would be smaller and could still do the additions. We need multipliers, which FPGAs put in the DSP blocks, but you could also have multiplier blocks here. So you kind of go, well, almost all my logic is in all this multiply accumulate for signal processing in wireless or maybe deep learning, okay? And that makes you think, well, this could be a good architecture. And that's logical. Does that make sense? FPGAs are also, though, they're not a static target. So if you go back to early FPGAs, they were all lookup tables and 1-bit routing. But now if you look at them, they have DSP blocks. So they have some of these coarse-grained function units. And the DSP blocks connect to the regular routing, but if you look carefully at them, you'll also see that they have some cascade connections, which are bus-based and have limited flexibility. Like they're very limited flexibility to just cascade DSP blocks together, and they do it like 32 bits at a time or even more sometimes. So you could think of it as parts of an FPGA. The DSP part actually look a lot like a CGRA, with also the single-bit FPGA routing coming in as well. So yeah, that's kind of the killer app for CGRAs, is usually this kind of DSP-heavy application. But FPGAs have also evolved to be better at that, which makes it a harder target. There's ongoing work. Some of the deep learning accelerators you could describe as forms of CGRA. Okay, so there's a company called Samba Nova, okay, which is, I think, raised the most money of any of the hardware startups for deep learning. And Samba Nova doesn't talk that much about their hardware, but their hardware appears to be a form of CGRA. And it makes sense that this is like the target market where you would go after it, because spatial is efficient for repetitive calculations, but if you're doing deep learning, you know your repetitive calculations are multiply accumulate. So maybe you can make something that's a lot like an FPGA, but more efficient because you pulled out the 1-bit routing and went kind of more completely bus-based. You still want to have, is it 8-bit, 16-bit, 32-bit? Deep learning uses different precisions. So what you usually wind up is you don't make the bus just 32, so you start putting some flexibility back in. Anyway, it's a good question. Does that answer your question? So I don't have time to talk about Samba Nova, and they haven't actually published much about it, but it is basically a CGRA from everything I can see. If you can figure out all the details, let me know. So, okay, that's all I had to say about routing architecture. So, and maybe what I'll do is we'll go through a part of the next lecture, which is where I should have been at the start of today, and then we'll take a break. But we'll go divide things up more evenly. We'll keep going. Okay, so I said that was the end of routing architecture, but I kind of lied. It was the end of general routing architecture. Now we're into kind of special routing architecture. Okay, So this is just a few administrative things. Are course evaluations open now or not? I can't figure this out. Yeah, it appears they're not open because we're at a 0% response rate, but it appears that no one can submit it. So it looks like it's a really late, as far as I can tell, it looks like the evaluation period might be December 8th to 21st. Does this actually make sense to people? Have they seen this or not? All right, this is the latest evaluation period I've ever seen, but assuming that eventually it becomes possible to submit a course evaluation, again, I appreciate it, give you some suggestions. Okay, we talked a bit about when is the last lecture. So today's the last lecture. Last year I somehow managed to fit in one more lecture. I'm not entirely sure how that happened. Maybe I started a week earlier. So I have one more lecture on time domain multiplexed FPGAs, soft errors. So FPGAs are actually subject to radiation-induced errors, and there's some interesting techniques to mitigate that. And different programming elements. We've mostly talked about, we've talked almost exclusively about SRAM, but there are FPGAs that use flash and other things. So I'm going to post the slides and the videotape lecture from last year. I'll post a question on Piazza. Does anybody want me to do this in person? Probably won't do it if there's only one. You can just watch the video, but I'll put up a poll. If a bunch of people want it, then I'll come next week. Otherwise, you can just watch it, or you can study for exams. Your call. So. This is the background reading that we'll talk a bit about today. It's kind of incorporated in what I'm talking about. And the final reading. So, one of them is another one of the very recent FPGAs. So Agilex from Intel talks about some of the layout-driven patterns that I talked about. So it's interesting. And essentially some of the decisions that they're changing from Stratix 10. So we'll talk a bit about Stratix 10 delay, and Agilex kind of changes some of those. And the other one is one from Microchip. Another FPGA vendor that makes non-volatile FPGAs. They make them out of flash. And this is the most recent paper they have on how do they make FPGAs using those non-volatile elements. So the chips work differently. So it's kind of an interesting paper too. And there are some advantages to making them out of flash. Like these chips, they don't lose their memory. When you turn on the power, they know what to do. And in theory, they can save some area based on not having SRAM. But they have the challenge of their process technology is not as standard, which means it's harder to put them on the state-of-the-art manufacturing technologies. So anyway, so if you haven't finished your quota or you just want to keep reading, there's one more chance to submit 2 more summaries. Okay, so let's talk about clocking architecture. Okay, so we've talked a bunch about logic and DSPs and routing. We also need to get clocks to our flip-flops. So, so do we have to do anything special for this at all? Because we have all this programmable routing in our chip, and it can connect anything. So it can connect up our clocks too. So what do you think? Do we need anything special for clocking, or could we just use the regular routing? What do you think? Yeah, so that's a good answer. I'm just going to repeat it so people, in case anybody couldn't hear it. You could make a clocking network out of the regular routing, but it's not going to be a very good clocking network. You want something that's basically balanced delay. The main purpose of the general FPGA routing is trying to make low delay connections and also not take too much area. The goal of a clock network is different. It actually doesn't care that much about delay. Lower delay is better, but it's almost as a tie break. The main thing a clock network wants is all the registers on this clock, we want to have the same delay to them. And that is kind of fundamentally different than I just want to get the minimum delay. You could write an algorithm in a new FPGA router that tried to construct out of the regular FPGA routing topologies that were skew balanced. I have the following 10,000 things to get to, make me connect the wiring in a way so that you get the same delay to all of them. And it would be better than just not trying to write that algorithm. It still wouldn't be great because basically the routing architecture is not optimized to try to build those kind of balanced trees. Does that make sense? So yeah, all FPGAs include special clock networks. So if we build them out of regular routing, we need to write a low skew routing algorithm. So we need a new, but that's okay. We could do that. Lots of CAD engineers just pay them enough money, they'll write it. Okay, so it's going to take some non-recurring investment, but that's okay. But you still won't get a really low skew topology because the switch patterns, et cetera, aren't optimized for it. And there are other issues. Is there anything else besides that? These are big issues, but anything else that you kind of also causes problems? Maybe this is a hard question, so I'll just tell you the answer. Crosstalk will add jitter. So does everybody know what I mean by crosstalk? So does anybody know what I mean by crosstalk? Maybe this is a bad question. Yeah. What is that? What do I mean by that?
So I think it's like if you have two wires parallel,
Yeah.
close to each other, if you have one like positive edge on one wire, you may influence another one.
Yeah, exactly. So I've got two wires. They're running parallel to each other. So that's wire 1, that's wire 2. And this happens all over the chip, right? You got wires everywhere. There's a capacitance between those two, fairly significant. If basically the driver of this sends a waveform in where the waveform rises, that is basically capacitively coupled to this wire, and its waveform will also rise some, okay? Eventually, this driver, if it's trying to keep it at a 0, it'll go back down to 0. But it basically can inject some charge into the other wire. What that means is that it can change your delay, okay? So the delay of this wire is not just a function of, well, it is partially a function of what's going on in this wire beside it, okay? Its delay will change some. For regular routing wires, like when you're just routing from one LET to another, the way the CAD tools handle this is they basically add some extra delay. They say if this other wire was switching in the opposite direction, it'd slow you down, so add that delay, okay? For a clock, you can also do this. You can say, well, this other wire might be changing at the same time, but you basically have to be conservative and say you might get sped up, you might get slowed down, depends on what all the wires around you are doing. That hurts you more on a clock. The reason it hurts you more on a clock is that's basically clock jitter. That's uncertainty in when your clock edge hits. And you have to actually account for that. They have to account for the worst case of the clock could be this slow or it could be this fast. And remember, we have to analyze both setup and hold. You get hurt by every change. The more uncertainty there is in the clock, the harder setup gets and the harder hold gets at the same time. So uncertainty in when a clock edge hits is worse than uncertainty or extra delay that you have to assume on just a regular data path routing wire. So we don't like this, crosstalk adding jitter or clock uncertainty. The other thing is the regular routing is optimized for area and speed. It's not optimized for process uncertainty. So what I mean by process uncertainty or variation is, you say that the wire should be a certain width, and you say that the transistors driving it, should be a certain size, and a certain threshold voltage. But there's variation in all those things. Again, for your regular FPGA routing, this is all handled by essentially adding some extra margin. The most important thing for the regular routing wires is the setup constraint, the maximum delay. So you add some extra delay. For clocks, you basically have to widen the delay range again. You have to say it could be this fast, it could be this slow. I have to basically model both cases and see if either of them could cause a setup or hold violation, which basically makes everything harder. Slows your chip down, also gives you more hold violations to fix. So what you do in clocks is you actually make the wires extra wide and you make the transistors extra big. And that costs you area, but it reduces variation. It reduces variation because you've got a smaller percent difference. Usually your variation is my transistor width could vary by, 2 nanometers. So that's a lot if your transistor was only 20 nanometers wide, but it's not that much if it's 200 nanometers wide. So if you're willing to spend the extra area to make things bigger, your percentage variation goes down. And for clocks, we will do that. We want the clocks to be fast until we really know their delay. Okay? So the skew is going to hurt either setup or hold, depending on which direction the clock skew is between the source and the destination register. And clock uncertainty, which is these two, is worse. It hurts both. Like I just don't know where the clock is, so whatever analysis I'm doing, I have to add some margin. So it hurts you everywhere. Does this make sense? Okay, so what does that mean? So it means that we really would like a special programmable network for clocks. One thing we could do is we could build an H tree for every clock. So who knows what an H tree is? You heard of this before? Okay, so some people, not everybody. So this is an H tree, and it looks like a whole bunch of H's, so it's really easy to remember. It's a skew balanced structure that's commonly used to distribute clocks. So here's my drive point. I'm driving a clock into here, and it goes out along this wire in both directions. Then it goes through a buffer, right? I don't want to have too much wiring hanging off one drive point, so I buffer it. And then it goes, vertically on both these. And it's a fractal pattern. Then it goes horizontally and so on. And the registers that listen to this hang off this last pit, okay? So what does that mean? It means a register that is here, which is actually pretty close to my drive point. So this register, if I just went straight from the drive point to it using regular routing, that'd be pretty low delay versus this register way out here. But in an H tree, they basically both have the same amount of wiring and the same delay. So the path is go here, go here, go here. One of them goes over this way, the other goes this way. And basically got about the same amount of wiring, same number of buffers, same amount of delay. And you can see how this is different. We're intentionally actually using some extra wire. Like we could have gotten to this register with less wire, but we don't want to. We want to get to it with exactly the same amount of wiring and buffering and delay as everybody else. Does that make sense? So this is a standard topology to make low skew clocks. In an FPGA, we could basically build a bunch of these H trees. Just build them, put them in the chip. We need some programmability. So in an ASIC, you'd be done. You'd build these H trees and you're done. In an FPGA, you need programmability. So what we do is we would put a multiplexer controlled by some SRAM cells at the drive point. So this lets us choose, what's the clock input. Maybe we take it from regular routing. Maybe we also allow phase lock loops to drive into it. We could do both those things, send them both into the multiplexer, and that's probably the best solution. And now we've got a clock where we can choose the clock source. Now we have to build one of these for every single clock. Okay, you can't put two clocks on this. This will take one clock. So we can do this, and actually small FPGAs commonly do this. Are there any downsides to it? I'll give you a hint. I probably wouldn't ask if there weren't any, right? So it's kind of a leading question. But it's not a bad thing. We are going to use this idea, and if we're building a small FPGA, this could be it. We're just done. This is exactly what Rapid Silicon, which is a startup that automatically lays out FPGA fabrics for you, and you can embed them in a larger design. This is exactly how they make their clocks. Yeah?
Just like hierarchical FPGAs, these are more scalable, I would guess.
Yeah, that's a good question. I mean, you can make them cover a really big chip, but they do get more area. Like as the chip gets bigger, the H tree gets bigger. But you do use them even for really big chips. So they don't run out of gas that way. I guess the basic reason is because we don't care what the delay from here to here would be. We just want them to be the same. Like it's like the problem is different. We will take whatever delay we need to get from this point to the end points in order to get just the same delay everywhere. So the basic problem is, what if I have a lot of clocks? If I have a small number of clocks, this is perfect. Okay? Okay, so I should say the good things. So H trees are low skew. We can shield these wires. They're now special wires. So what you do to minimize crosstalk is it costs you area, but this wire, for example, we lay out, and then you actually put a grounded wire or a power wire on both sides of it. Okay, so now what's beside it and is capacitively coupling to it will not switch. We won't get any crosstalk. We reduce the delay uncertainty of this wire. The way you normally do this is the clock wires go high up in the metal stack, and they're interleaved with your power and ground. So you need to distribute power and ground through a whole bunch of wires anyway, so you put the clocks in amongst them so that they're beside the power and ground and they're shielded. And because these wires are kind of long and you actually want to make them wide, they kind of make sense to put high up in the metal stack too. Does that make sense? And then to minimize variation, we also use wider metal, bigger buffers. These things all kind of fit together with put them high up in the metal stack. So all that's good. But the bad is, we can have more than 100 clocks in an FPGA design. Building 100 H trees gets pretty expensive. So a lot of those clocks are near the IOs. You know, PCI Express, DDR, SONET is an optical standard for communications, etc. So a single, I haven't checked like DDR4, but a single DDR3 interface in Intel chips, depending on exactly which protocol you're using, needed 5 to 7 clocks. That's just to talk to one DDR chip. And you go, why do you do so many clocks? Isn't that kind of crazy? You know, it's because you're doubling the rate of the clock. You're using one clock to send data, another clock to receive data, another clock for the commands. So there's clocks all over the place. And yeah, and it's not just because the designers are kind of, I had one summer student who just could not get his head around this. He was a great summer student, but he kept going, I got taught, he was taught in second year, always put everything on one clock, so he just couldn't get his head around this. But why are they so useless? Like, why are they doing that? Just put it on one clock. But they're not useless, sometimes you just can't avoid it, okay? You get a few big ones. So your major system clocks where you're doing most of your processing, there usually aren't too many of those. There might be one, there might be 3 or 4. You know, if you have 100 of those, you probably are a bad designer. But you do get a lot of these other smaller ones, especially near the IOs. So if we pre-build 100 H trees, it gets expensive. And where it gets expensive, well, you get 100 wires per channel if you want to make 100 H trees. So what is actually expensive is like the last part of this network. So I haven't actually shown it, but if I keep going down, you're going to get more wires near the end of the H tree, if that makes sense, right? Eventually, you're down to like 1 wire per row. And that's actually where it gets expensive. To have, you know, 100 wires is not a big deal. If you just say I got 100 wires in the chip, that's nothing. 100 wires per channel is a lot. So what you care about is not the route, because you literally would have 100 wires there. It's down here near the leaves where you've got a wire for every single row. And if you have 100 of those, that actually is a lot, okay? So, you know, a typical channel width for a commercial FPGA is in the 200 to 300 to 400 range. So if I add 100 wires per row for the bottom of 100 H trees, like the leaves of 100 H trees, that's actually a lot. Especially because I said it's also good to make them on extra wide wire and to shield them, which makes them extra expensive. So you could do this, but you're going to kind of not like it. So any ideas? What can we do to make this more efficient? Like the idea of an H tree is not a bad one, but can we make it more efficient? Yeah, what do you think? So, so you're saying fewer clock trees, so I like that. Let's build fewer clock trees, or fewer leaves in particular. It's the leaves that are killing me. Having a lot of roots isn't too bad. Yeah, okay, so maybe we don't have to build the last little bit of the H tree. Maybe the skew is small enough that the last little bit we won't build as an H tree. So that's a good idea. So if we do that, that's where most of the area is. We can get a bit cheaper. Maybe the skew is still acceptable. Maybe not perfect, but it's okay. So yeah, that's a good idea. Any other ideas? Yeah? Change the topology? So what do you mean by that?
Is there a better, better than the H shape?
So one of the things FPGAs do is near the leaves, they often do change the topology, okay, to something called ribbon spine, which has higher skew but less wire. So that is one idea. Near the leaves do that. I guess another thing you could do in terms of topology is why build 100 H trees that go all over the chip if you're never going to use, if you can't really have 100 system clocks, right? Like you've kind of built 100 huge clocks and you can't have 100 huge clocks. You can have 100 clocks, but they're not all going to go everywhere. Does that make sense? Yeah, so you have a thought or no? Okay, so basically FPGAs combine all these ideas. So the first idea is build some big and some small networks. We need a lot of clocks, but it's kind of fundamental. They don't all have to be huge. So here's one that's used in, for example, a lot of Intel FPGAs. So you build 16 of these H trees that go everywhere. Okay, so this is like not one H tree, it's like 16 of them. And then I also build 16 quadrant H trees. So what is a quadrant H tree? It's basically an H tree that looks just like this one, this black one, but I've just, instead of I basically made a drive point for it in each quadrant. So it's almost the same. I just basically have to put a drive point, which means a routing mux, in the center of each quadrant rather than the top. Okay? And basically the wiring that I need for one of these quadrant H trees is like a quarter or a little less than a quarter of what I need for a chip-wide H tree. So if I build some chip-wide H trees and some of these smaller ones, in the same area budget, I get more clocks. Okay, so in this case, for an area that's somewhat less than what 32 full H trees would cost me, I can get 16 H trees that span the chip and 64 that span quadrants. So this is a better trade-off if I don't need all huge clocks. If I need a mix of some big clocks and some little ones, this is a better way to do it. Does that make sense? And usually they don't stop at this. They'll also make some that are even smaller, particularly around the IOs. So now you kind of prefabricate a mix of sizes. So that's the first trick. The second trick that is used by both Xilinx and or AMD and Intel is muxing at the bottom level. Okay? So most of the expense of this is not the top of the H tree, because there's not that many distinct wires there. It's just as it branches out into like these little capillaries almost, that's where you get most of the wiring. So let's go back to our example where we have 16 global clocks and we have 16 quadrant clocks in each of our 4 quadrants. So that's cut us down from 100 H trees down to the area of about 32. That's what we've gotten to. Most of that area is still the fact that we need 32 clocks, like 32 wires at the leaves of our network. But what you can do is you can say, well, once I get down to just a small number of logic blocks that this piece of clock is feeding, there probably aren't 32 different clocks. I don't know which clocks they might need, but they probably don't need 32. So I could multiplex it. I could say I'm going to have essentially another routing switch, well, a couple of routing switches here, that allow me to choose from those 32 possible sources of clocks that have gotten pretty close to my logic block, but not all the way. I can pick a few, well, what Altera calls row clocks. And in Altera chips, it's 6. So you can pick 6 of these row clocks, and they literally cover part of a row. They go through like about an eighth of a row. And in theory, you could wind up with the logic blocks there actually want 32 different clocks, so there's no way to get that down to 6. But it's statistically unlikely because the logic there has been grouped because it kind of belongs together by the placement engine. So what you do is you also change the CAD tool, so Quartus or Vivado, to also put a constraint in it. They count clocks as they're evolving the placement, and Quartus, for example, will not allow this region, which would correspond to like 1/8 of one row in their architecture, to have more than 6 clocks. If a change to the placement would actually result in more than that, they just won't do it. Okay? And that turns out to be a pretty loose constraint. If the placement engine now had to do lots of weird things, like it had all sorts of, it really wanted to put these things there that use 10 clocks, and now it can't, and that's going to mess up the design, that would be bad. But it turns out, because we did experiments on this, if you just say it's 6, it's fine. The placement engine will forbid a few things. It can find alternatives. It's okay. Okay? Does that make sense? So it's kind of done 2 things. It's changed the topology. The bottom of the topology has changed from an H tree to what's called a spine and rib. So it's basically like this is called a spine, and these are called ribs. It's higher skew than an H tree, but as long as you don't make the spine or the rib too big, it's still not too bad. And then an extra trick is to actually do this muxing, so you don't need that many of the ribs, and tell the placement engine about it so that it doesn't create illegal placements. Does that make sense? Okay, so that was the state of the art until Stratix 10, at least for Intel chips. Stratix 10 uses the same idea for most of the H tree and for the spine and rib. The one thing it changes is basically instead of saying I've got 16 of these H trees that can go all over the chip, and then I have 4 groups of 16 that each span a quarter of the chip, they went, well, what if we put a little bit of programmability in there? We took all those wires that we shielded and we've made them really good for clocks, and we, instead of having just buffers, we put a bit of muxing in there so that we could choose how to connect them. Then we could make 16 clocks that span the whole chip and 64 that are each in a quadrant, or we could make 32 that span the whole chip, or we could make some irregular ones that overlap in weird ways. So we'd basically be able to build H trees, but we wouldn't have to build H trees. So that's basically what they did here. You can think of this as these are now, they've made special clock wires again. They have programmable switches that connect them together, and the switching pattern is optimized that it's really good at building H trees. Okay, so it's easy for them to build H trees. And then once they get, that's done at kind of the top level of the clock network. Once they get down near the bottom, it's basically goes back to it's less programmable. It's H trees and these ribbon spines, right? So they kind of build the bottom the same way they did before, but they've got some more programmability at the top level. Does that make sense? What it allows them to do is they can do stuff like this. Like they can go, well, here's a clock. It's pretty skew balanced, but I only needed a sort of a part of my H tree. So I only built a part of my H tree, and then I could build this other piece of another sort of irregular H tree using like in another part of the chip. And I can basically, with the same number of top-level clock wires, I can fit more stuff in many cases, right? Like if I didn't need to build clocks that went everywhere, I can just kind of build them to order. They needed to write an algorithm that could do that. And as I said, once they get down to the bottom level, they do the same spine and rib clock that I just talked about. So the bottom part just looks the same. Does that make sense? Okay. Okay, what does Xilinx do? Xilinx at a high level is pretty similar, although they tend to rotate everything by 90 degrees, which means I'm not going to use all their terminology because you kind of have to rotate your head by 90 degrees and then go, this is kind of the same. So yeah, to first order, same idea. They do a clever thing in their 14 nanometer FPGA and below. They realized that kind of near the, not at the very bottom of the clock tree, but towards the bottom of the clock tree, instead of just putting buffers in, what they did is they put in a programmable delay circuit. Okay, so that's what this is. They have a programmable delay, an AND gate, and a mux. So what's the AND gate for? The AND gate is they can actually clock gate. So they can actually turn off this part of the clock. That's to save power. So if you know that nothing on this part of the clock is going to do anything useful, and you care about power, gating the clock saves your clock power. Because clocks are toggling all the time, they can actually take a fair amount of power. Remember that you burn power when you're charging and discharging, when you're toggling. So you don't have to clock gate for functionality, because you can always just use the clock enable on the flip-flops, and that's what normally happens. But you can save some power if you know that a whole bunch of registers are going to be disabled to actually use this AND gate to disable the clock. So that's why it's there. The time borrowing circuit is, this is what the time borrowing circuit is, or time delay circuit. You've seen this a few times. This is a common structure in FPGAs. You build a chain of inverters that is basically just delays the signal, and then you build a mux that lets you choose how many inverters do you go through before you go to the output. Okay, so I'm ignoring this AND gate because that's just for gating, but I can now delay my clock. Okay, so why would I want to delay my clock? The reason is to, well, intentionally delaying a clock. It's the same idea as we saw with the pulse latches that Intel put into Stratix 5. If I can shift my clock to some registers, I can basically stretch out some transfer that's giving me problems. I'm failing setup time on it. It makes the transfer after that harder, but it can make a certain transfer easier. So Xilinx put these in so that they could actually delay clocks to groups of registers in order to do some time, what's called time borrowing. Make this cycle longer for this logic. Does that make sense? And this is most useful on high-speed clocks because you usually shift by only a few hundred picoseconds. So on a clock that's 50 50 megahertz, that doesn't help much, but on a clock that's 500 megahertz, that might be quite useful. Okay, so the way it works is they have a clock coming by, and they can actually they can basically choose the no delay path through that circuit. So to send it straight to the mux, it doesn't go through any of the inverters. That's the path they pick. And that's kind of what they do by default. So they'll do that, and they'll send it into these logic blocks. But they have more than one of these kind of clock ribs, the last stage of clocking, that goes by a certain group of logic blocks. So they can send another version of the same clock where they've actually delayed it some. Okay, so here they've actually turned on this variable delay circuit. They've sent it out through another one of these ribs because they had another one left over. It was not used by a different clock. And they send that to this logic block. Okay, so if I had a register in here, that went through a bunch of LUTs and eventually went into this logic block and to a register there, and I was having trouble meeting timing, like that transfer was too slow, then this can help me. And it doesn't have to all be in this logic block. It could all go out through a whole bunch of routing and come in too. But for some reason, I'm having trouble making this fast enough. Delaying this clock by, say, 300 picoseconds gives me another 300 picoseconds of allowed delay from this register to this register. Does that make sense? Okay, so it gives them another optimization hook. And it's pretty cheap because they just put the delay circuits in the clock network when they're essentially choosing the source for these clock ribs. They already had multiplexing in there because it's just like Intel. They want to go from a bunch of spines to a smaller number of ribs. But now they just put a little bit extra. We're not going to just pick which clock. We'll also pick if we're going to delay it or not. And it gives them another optimization hook. Okay? It's not free. When you do this, your setup time between my hypothetical register and between these two logic blocks gets better. My hold time gets worse. So I got to make sure that's okay. And if whatever is fed by this register, that transfer is going to get harder because I delayed the clock. So time borrowing really is a zero-sum game. You make one transfer easier, another one harder. But these are the results that they got. They basically looked at what if they also changed the pulse latches. So they changed their registers to pulse latches just like Intel did. And they got some gain by doing that because the pulse latches are faster. And they can get more gain if if hold time is not a big problem, then they can get more gain by widening the pulse, just like Intel did. But they basically show that if they, instead of using pulse latches, they basically use this delay the clock technique, that they can actually get a bigger gain. Okay, so they can get, if hold time is pretty difficult, that's what this means. They don't have much margin at all. They can get about 5% speed up. If their hold time is easy, they can get maybe 7%. If they do both, they get a little bit more than either one. But they basically argue that this ability to delay the clocks is actually easier to use to do this time borrowing than pulse latches. They both can do it, but they like the clock skew as their first technique, which is a little different than what Intel did. Does that make sense? I know this is kind of detailed, so hopefully this is like a teaser. Go read that ultra-scale paper. This is one of the interesting things they did in it. Okay. Okay, that was Xilinx's 14 nanometer part. Versal is their latest one, 7 nanometers. And they did something pretty interesting in Versal. So this is, sorry, let me go back to that. Okay, so this is the frequency. And this is what fraction of the clock period the clock skew is taking up. So as we go to higher and higher clock speeds, which people want to do and FPGAs are supporting, they're getting faster and faster. So you actually have a fair number of designs that are up in the 500 megahertz range now. The clock skew is 5 to 7% of your clock period. And this is with low clock skew networks. Like they've built those H trees at the top level, and then they've built the spine and rib at the bottom level, and they've shielded them. And despite all that work, so they've already done everything they could, they're still getting a skew of 5 or 7% of their clock period is gone. So, or more actually. And the reason is process variation. Okay, so if every transistor, every wire did exactly what it was supposed to do, this wouldn't happen, but they don't. And the process variation is getting worse as we keep shrinking things, even though they're trying to control it in the clock by making the wires thicker and so on. So they did a clever thing. They go, well, we've already got these variable delay chains on our clock network. We did that because we like it to make our designs faster. Could we use that to get rid of the skew? So what do you think? I'll give you that as a thought experiment. Do you think, how would you do that? It's kind of an interesting thought of, so I guess the answer is they can do that, but how? What would you do to make this work? It's kind of a hard question, but it's always useful to kind of think, like, if somebody comes up with something clever, like, could you come up with it yourself? Yeah, so that's the basic idea. They can't do it, in their original, like they can't bring the process variation to zero, right? So there's nothing they can do of like, well, relay out the clock, et cetera. Like they've already done all that. And there's still process variation. But what they can do is after the chip is manufactured, when they're testing it, they can try to measure the clock skew and then program the delay chains to cancel it out, okay? So they have this extra knob. And that's what they do. So the Versal paper talks about this a little bit. They don't give all the details of how it works, probably on purpose. This is an interesting figure they have it. So they're basically, all these different colors are showing the clock delay to different parts of the chip on one clock network. So ideally, it would be like the same, okay? Like there's no skew. No matter where you are in the chip, the clock arrived at the same time. But they intentionally didn't put any axes on this, and I asked them what are the units, they go, I can't tell you. Well, the units are time, but the numbers are not visible. So wider is bigger by an unknown amount. What they did is they added phase detectors at the boundaries between clock regions. So clock regions are kind of like the upper parts of the H tree. Remember, at a certain part, after you've gone down the H tree a few levels, you go to this ribbon spine structure that's a bit cheaper. So right where they're doing that, they call that like a clock region. And they put phase detectors on the boundary. So they've got two different clock regions, and in between them, you can put a little circuit that actually takes two clock edges in and says which one arrived earlier. It's not that hard to do, okay? So you can do it as a thought exercise, could you make that? But it's possible to make that. And they put those between, every pair of adjacent clock regions. So when they turn the chip on, all of these phase detectors basically say which clock's arriving faster. And they're doing it for all the different clock networks. And they adjust the delay chains that are right beside them, that are selecting this last stage of the clock network that are going to the ribs until they basically have aligned with their neighbor. And it turns out that if everybody aligns with their neighbor, and they keep doing that for a while, that it also aligns everybody globally. There is actually no global matching. It just arises because everybody's trying to match their neighbor. And eventually that arrives at a pretty good global matching. So they said that this typically cuts their skew by about 60% versus non-adaptive clock networks. So it's a pretty clever technique. It leverages the fact that the FPGA is already programmable. So they already put programmable delay chains in their clock network. They already have this muxing in it. So they throw in these phase detectors. And they might not even actually build I'm not sure whether they actually build the phase detectors or just when they're configuring the device, if they just program in phase detectors and use their actual programmable logic to do this. But whenever you're programming the device, it goes and figures out all of the clock misalignments and adjusts these delay chains to take them out. Which is a pretty clever use of the programmability of an FPGA. And this clock skew keeps getting worse, right? Like as we make chips, as process variation gets bigger and as clocks get faster, this basically consumes an ever larger part of your clock period. So it's actually nice to have a solution to it. Okay, so that's all I had to say on clock networks. Why don't we take a break until, I guess, 5:47. Sound good? People came up with some very good solutions. So I guess my reference solution, which I tried hard on, I was reasonably proud of, gets an average area of 2.07 times 10 to the 8th on that Stratix 4-like architecture. So I'll give honorable mentions to Ziwan, Yufeng, and Taiken, who all either matched or came very close to that. Third place is Yifan Yu, who beat my solution. So well done. And Jiaxin, apologies if I mispronounced people's name, but Jiaxin Zhang beat my solution by a little more. So it got pretty tight near the end here. So that was second place. And then 3 people were so close that I just decided it's a tie, okay? Because differentiating by 1 part in 1,000 seemed like too hard. So Jackson Rigby, Jiqi Zhao, and Li Chen Liu, all from 2.035 to 2.038. So you're all tied for first because I just don't have enough precision. No photo camera. So well done, all of you. So good job. And I promised Amazon gift cards. They are coming. Okay, so for everybody, honorable mentions. Well done, but your reward is the recognition. Okay, and you can, that's always the best reward. So maybe you're the true winners here, right? But first, second, and third place, I'm going to send you Amazon gift cards. I went over to the bookstore, and they're sold out of Amazon gift cards. I said, really, what happened? They said, the Department of Electrical Computer Engineering came in and bought them all. All right? I said, oh, that's my department. So anyway, but I will do some electronic ones and mail them out to you since this is the last lecture. So anyway, great work. Well done. It's actually not an easy algorithm to get good answers. It does get exponentially harder, basically, to get better and better answers. So this is actually significantly better than my solution because it's like it would be hard to tune it up to get that last bit out. So good job. Okay, so that said, we've got another 40 minutes of content. So I'm going to see how much I can get through. Let's see. Okay, so that's where we are. Okay, so multi-chip integration. So this is, yeah.
I have a quick question, about the H structure, the H-shaped cloud structure.
Like H trees? Yeah.
Yeah,
Okay.
I saw there was the black part and the red part. I just want to know.
Oh, what am I doing with this? This is just a trick of take a big network, like these black ones represent an H tree that covers the whole chip, and the red ones are smaller H trees that cover a quarter, like a quadrant. And it's just to show you can fit in the same silicon area 4 quadrant trees that you get for 1 big chip. And this is exactly what a whole bunch of Intel chips do, where they actually do build quadrant ones and full ones.
Are they connected?
No, they're not connected because you don't want to connect. These are all separate, distinct H trees. They only connect in this last level where you have this muxing. Okay?
But how the red part connects?
Oh, yeah, that I should draw. Okay, the red part actually has a mux as well. So that's just poor draftsmanship by me. It's got the same kind of mux. Because you're right, every one of these clock networks has to have some programmability of how to get to the drive point. So I didn't draw it, and that's just kind of my mistake. Does that make sense? Because you're right. Otherwise, it's just a clock from nowhere, and you can't do that. So, and what goes into those muxes is usually you send in, some signals from the regular programmable routing because that lets you make anything a clock, and then there are usually also some dedicated connections from phase lock loops and a few special IOs because those are common sources of high frequency clocks. But it's a good idea to have some inputs from the regular routing because if you can think of it, somebody makes a clock out of it. Like there were some Altera chips where I wrote the CAD tools for them, and there was no path from the regular routing into the clock network because it was like, well, why are you doing that? You should take it from a PLL or one of our special clock IOs that is more designed for fast clocks. People do all sorts of stuff to make clocks. So that was a bad idea because there'd always be somebody who wanted to make a clock from something else. Anyway, it might be more answer than you wanted. Okay, so the next thing I'm going to talk about is multi-chip integration. So in an FPGA context, and FPGAs have done some pretty interesting things. They've been some of the leaders in kind of going beyond one piece of silicon. So some of this is about just how do you do multi-chip integration, but obviously in the context of FPGAs. Okay, so the first company in the FPGA industry to do this was Xilinx. And their idea was, instead of making one big FPGA, which I'm showing here, so you can see there's different resources, like the yellow is I/O, blue is logic, and so on. What if we made that out of multiple chips? Okay, so, and a nice thing about an FPGA, if it's laid out in columns, is that it's vertically the same. So they could actually make one chip and replicate it 3 times and make this big chip, okay? So they don't even have to make 3 masks, which are expensive. They can make 1. So the advantage of this is that you get better yield than a huge chip. I'm going to show you a yield model in a second. But the basic idea is this chip, if you can't repair it, and Xilinx can't repair their chips, like most logic chips, if you get a defect somewhere, you throw the whole thing away. And the probability of getting a defect obviously gets higher as you make your chip bigger and bigger. You just need something to go wrong. Little tiny speck of debris, some little flaw in the photoresist, whatever, that chip's dead. So if they can make it out of multiple smaller chips, they get better yield. And when Xilinx introduced this was at 28 nanometers, and the largest chip they could make using this technique. So they called them 2.5-dimensional FPGAs, or I guess the industry calls them that. I'll show you why in a second. They could make something with 2 million logic cells. And the largest FPGA that didn't use this technique was 1 million. Okay, so Xilinx made one that was 1 die, and they could make another one that was made out of multiple dice, so it was twice as big. So you could make a bigger chip. And a bigger chip is useful because some people will pay a lot of money for the biggest FPGA available. Like, they're pushing the boundaries of what can be done in a system, and they need the best chip. If you have a bigger chip than anybody else, you can kind of charge an awful lot of money for it. So it's nice to have the biggest chip. The other thing that's good about this is you save mask costs. So they actually make a mask to build this chip, and if they take 3 copies of it and integrate them together in a system, they sell that to you for as a 1.5 million logic element device. And if they take 4 of those little chips and sell it to you, that's a 2 million one. Normally, they would have had to make 2 different masks for that, but they didn't have to. So they actually were able to fill out the top part of their product lineup with fewer masks. And because masks are expensive, that's good. But it needs to be better than just combining multiple chips on a board. Because you can always just buy a bunch of smaller chips, stick them on a board, wire them together. So if it's not better than that, there's no point. And Xilinx used this for the first time at 28 nanometers, and they've continued using it. So they've used it all the way through to their Versal 10/7. I mean, that's a sign that they like it, right? So you'll see some things. If you see something in the industry where it goes in one part and it comes out the next generation, it means probably it was an expensive mistake. It was a good try, but people now don't think it was a good idea. If it goes in 3 or 4 generations, they think that this is a great idea, and they're continuing to build on it. Okay, so how does it work? So the first chip they did this in is Vertex 7. That's where this figure comes from. They call those chips that I just showed you super logic regions. So that just, SLR means this thing, okay? An FPGA. And their biggest device in this generation took 4 of those. Okay, so I got 4 of these. And what they do is they put micro bumps on the top of them. Okay, micro bumps are solder bumps, but they're really close together. You can get them within about 30 microns. Okay, so pretty tight. That's a lot bigger than the distance between just vias or wires, but it's a lot less than the usual bumps that you put on top of a chip to connect it to the package. Okay, so if you look, this is like a zoomed in version. So on top of their chip are these micro bumps. So little solder bumps that are on top of pieces of the top level metal. They take that and they mount it upside down on an interposer. Okay, so this is the interposer here. Okay, so does everybody know what an interposer is? Have you heard that term? How many people know what an interposer is? Okay, so maybe 1 or 2. What's that? Yeah, it connects multiple dice. So an interposer is made out of, well, usually they're called silicon interposers, or at least I should have said that. So silicon interposer means it's made, sorry, I shouldn't do this for people at home. A silicon interposer means it's made using silicon manufacturing technology. So this is another piece of silicon. Let me erase that. So this is your FPGA. It's expensive, uses an advanced processing manufacturing process. You've mounted it upside down on top of the silicon interposer, which is another piece of silicon. Okay, it also, it's silicon you can put pretty dense interconnect on. You can put the wires very close together compared to what you can do on a circuit board. So what Xilinx has done is they use the silicon interposer. It's not as advanced a manufacturing process as the FPGA. So in this generation, they were using a 28 nanometer FPGA, and the interposer is 65 nanometers. So 2 generations behind. And the silicon interposer they're using has only metal, no transistors. Okay, so but they can make the metal much closer together than they'd be able to make on a circuit board. A circuit board is made, in some ways it's similar to the way you make metal on a chip, but all the manufacturing tolerances are just orders of magnitude worse. Okay, so the density of interconnect you can get on silicon interconnect is much, much higher than what you can get on a circuit board. So they've got a lot more wires on this silicon interposer. The limiting factor in how many wires they can connect to are these micro bumps. These micro bumps are the biggest thing. And they're about 30 micron pitch, which is still pretty tight. So what that allows them to do is have a whole lot of wires connecting these different FPGA dice. Many more wires than they would be able to get if they just put them in separate packages and stuck them on a circuit board. Does that make sense? So that's what they gain. What they lose is kind of complexity. This is more complicated than making a circuit board. The last thing that you have is these big black things are called through silicon vias. So, okay, if you take a piece of silicon and you flip it upside down on another piece of silicon, they can connect to each other. So you can kind of see how you could, okay, the solder bumps connect to the wires, and that allows you to go out through a solder bump, through a wire, back up through a solder bump. So you can connect a lot of wires across these chips now. However, you go, where does my power and ground come from? And how do I get my IOs out to the printed circuit board, right? I need to get out to the package. This is the package. A package is basically like a fancy printed circuit board. Its manufacturing is better than a printed circuit board, but worse than a chip. And you go through the package, and then you come out on really big solder bumps that connect you to the circuit board. So it kind of all looks similar, but like the manufacturing fineness, pitch is getting bigger and bigger. Anyway, to get your power and ground to this chip, you need to actually have vias, so vertical metal, that goes right through the silicon. Normally you don't have that. You just have vias that are quite short, going through little bits of oxide. These are through silicon vias. They actually have to be etched all the way through the silicon, because otherwise you can't get power and ground into this, and you can't get any signals in and out. You just have like a hamburger with no ability to access the actual hamburger patty, right? You only have the bun. Does that make sense? But they can do that. Okay, through silicon vias are a lot bigger than these micro bumps, and then these what are called C4 bumps that connect to the package are a lot bigger still. So they can get about 10,000 of these micro bumps, you know, kind of in the region where the edge of the chip is. Okay, so that's a lot of wires that they can now have crossed between chips. The number of wires you can get out to a package is more like maybe 1,000, and they're getting like 10,000 in their latest generation, more than 10,000 wires going between these chips by using these silicon interposers. Is everybody with me? So, okay, so this kind of is a detail of what it looks like. This is I guess this is a 40 micron pitch in this generation. It's gotten a bit smaller since then. That's the FPGA. It's connecting to the interposer, which, as I said, is actually being used to wire the FPGAs together. There are some of these through silicon vias that get your signals to the package, get your power and ground, and then the package itself looks like kind of a high-end circuit board that gets you to the package outputs. So that's what the whole thing looks like. Okay, why did they do this? So it's pretty cool technology, actually, and Xilinx was one of the first, maybe the first company in the world to do this kind of integration. So I told you a few reasons, but the biggest reason to do this is yield. So this is a simple but pretty reasonable yield model. So this is basically working out what is the probability that a chip is going to work, okay? And it's exponentially decreasing with the area of the chip and the expected number of defects per unit area. So that makes perfect sense, right? The only way the chip works is if nowhere on it is there a defect. So as the area goes up, that becomes less likely. As the defect density goes up, that becomes less likely. Okay, and this is a picture of a wafer, kind of abstract, but this is like the edge of a wafer, and I've drawn a bunch of chips on it. Anywhere where I get like a dot, that's a defect. That chip's not going to work. So this is drawing a large 6 square centimeter chip. That's pretty big. Okay, you can make chips a bit bigger than that. NVIDIA makes ones that are like maybe 8 square centimeters, but 6 square centimeters would be a very big FPGA. And early in the manufacturing process, the defect density, this is a very closely guarded secret. No foundry is going to tell you this, but early on, a defect density of like 1 defect per centimeter squared is like a reasonable number, okay? That means your odds of a chip that big working are really low. You expect that 1/4% of your chips will work. So that's really bad. So for this example, a 12-inch wafer, you get a lot of dice on it. So even with dice this big, you're going to get over 100 dice. But because very few of them work, you actually only expect like 0.3 to work. So it means to make one working chip, you probably have to run 3 wafers. So that's really expensive. Does that make sense? So now, but there is a market for these big FPGAs. People want them. And they want them early. So this defect density will go down. So it's going to get better. But the industry is driven by design wins. You get them somebody a chip early, they do the design, and a year later or 6 months later, that's when they start shipping it in volume. So if you can get them chips earlier, you can win that design win. So you actually care about this time when the defect density is high and the process is very new. Okay? And I'll repeat this analysis later for like a smaller chip and when the defect density is better. Okay, but anyway, so let's say that I do what Xilinx does. I'm going to make the same size FPGA. I want to make it 6 square centimeters, so it's really big, really leading edge. But I'm now going to make it from four dice that are each 1/4 that size. So basically, all my dice are much smaller. The probability of being hit by a dot is a lot lower. If I go through that math, I'm going to find that actually, over 13% of my dice now work. And they're small dice, so I get a lot of them per chip, per wafer. So I get 66 working dice per chip now, or per wafer. Now I need to put 4 of them together to make this system, so I got to divide by 4, but I still get 16.5 working systems per wafer, which is like 60 or 55 times better yield. Now this gets reduced a little bit if the yield to connect to the interposer, like if that sometimes goes wrong, then I would lose some of these, but that's pretty reliable, right? It's turned out that the yield of that is very high. So it reduces things a little bit, but not much. And obviously the interposer adds some cost, but not, it's going to still be a huge winning cost, right? Now the equation for this is a little different for Intel because Intel can repair its chips. So the yields that I'm showing you are if you can't repair. If you can repair, like you can imagine here where you go back, if I can actually repair broken rows, at least in most of the time, there can be some flaws that can't be repaired, like a power ground short might not be repairable. Intel can actually get much better yields out of this, and that was why that redundancy is such a huge win. Xilinx doesn't have it, but this new technique that with interposers, gives them some benefits that are similar and some benefits that are actually even beyond it, like they can repair the IOs, which Intel can't do. Or not they can repair them, but basically the smaller dice mean they get better yield even on the IOs. Yeah?
So before this interposer technique, they had to order the small chip sooner than the bigger chips.
That's a good question. Usually what FPGA, well, at least when I was in the industry, what usually would happen is you'd make the mid-sized FPGA in a new family first, okay? And the reason is that's the one that tended to be the highest volume. And it also was a bit easier to manufacture because so it comes out on you target the new process and that's the chip you go with because it's going to be the most profitable. And then you roll out the other members kind of as rapidly as you can. And one of those will be a really big one. Uh,
For the launches, and basically they had to wait until that exit under goes down.
they wouldn't, okay, because there would be some customers that would just pay a lot of money for it. And also, if you wait, say you wait a year, saying the defect density is so high, I'm going to have to charge you a ton of money. If your competition will ship that chip for a year, they're just going to get all the design wins. And once people have designed in one FPGA, because the tools, the exact IP, they're not compatible, they don't take it out very easily. They actually very rarely take it out. What they'll happen is if they're not happy or they want a better price, the next generation they'll be talking to a competitor. But the ability to actually take one out in a design that's done is very low. So it means if you get them chips, and these yields here are so low that even if you just said, like, I know I'm not going to get my money back on this chip, but I'm going to make it back on the 10,000 or 100,000 that come after this, so I'm just going to give it to them way below cost. And these companies are smart. They'll do that. For a big company like Cisco, they're going to do that. This yield is so low that they just may not be able to get enough working chips to do that. Does that make sense? They might, but it's a risk factor. So, so they get big gains in yield, right? Okay, so I just did, the best case for this though. A big chip and early in the manufacturing process where the defect density is high. So what if we repeat this for a smaller chip and later in the manufacturing process where the defect density is lower? Like basically, engineers at TSMC appear to just be, and in Intel's foundry division and so on, like they are under a huge amount of pressure to push this down, right? So the defect densities start up here, and this is time. This is like when the process first comes up, you've got that defect density, maybe it's even worse for the first little while, but now it's at 1 per centimeter squared, and there's huge pressure to drive this down as fast as possible. So it never goes to 0, but it can be driven down in like a year or 18 months or 2 years, depends how fast they push it, to 1/10 of what it used to be. Which is actually really hard work, but this is what you get when you spend billions of dollars on optimizing your fabs. You have people looking at every possible thing that could go wrong and tuning it up. So if I do a smaller chip, so 2 centimeters squared is more like the mid-range FPGA. Those are like the most popular ones. They're kind of the best value in a way. And our defect density has gone down by a factor of 2. It's a year or 18 months later. Your yield is actually now very good. 82% of your dice work. Your die per wafer is 299. You could still make it out of small ones. So you could apply the same technique, make 4 half square centimeter dice, but it's not really a great idea. Your yield goes up to 95%. So you get a few more systems per wafer, but you have the extra cost of putting them on an interposer and so on. So this really makes sense for big chips, and it's really compelling early in the manufacturing process. Does that make sense? Okay. That's all the upside. Downside, what about the routing? Okay, so in this particular chip, that's the first one Xilinx did this for, they have 280 vertical channels. Okay, so 280 columns in the chip. Each of them has 210 wires, like programmable wire segments. So channel width is 210. They can't get all those wires across the interposer. So the interposer has a lot of wiring, but the solder bumps are big enough they just can't make a solder bump for every single one of those wires. They can get 48 of them across, which is a lot. Like 48 times 280 is over 10,000 wires crossing between these chips, which is a lot. But it's still only about 23% of the wires they would normally have going vertically. And the delay, that micro bump has significant capacitance. It drops down to the interposer. You can't put all the micro bumps right on the edge of the chip. You have to have some of them further away to get enough of them. So some of those interposer wires are, several millimeters long. So all that means that you have about a nanosecond of delay, which is, in this generation, was about 5 times the delay of a normal routing wire. So these are their 4 dice, 1, 2, 3, 4. And this is basically where those wires are crossing between the dice. So they've got a choke point whenever they cross between dice, and they've got extra delay. So there is a cost. They think they did a very nice job on their CAD flow. So their CAD flow, they basically don't make people do anything. They just basically treat it like one big FPGA. Rather than treating it as 4 FPGAs that you have to think about what's crossing, their CAD tools just handle it all. So it looks like a single chip to the user. Behind the scenes, well, I know they've done this. They modified their placement engine. So their placement engine understands that there are these choke points and is trying to minimize how much interconnect crosses them, but it's doing that invisibly to the user. And in most cases, it works pretty well. Their customers said that usually it was fine. If you're really pushing it, sometimes you would get routing problems, but usually it was okay. Okay, actually, and my group did some experiments where we modeled this in VPR. Basically, a whole bunch of wires are cut by an interposer. What happens? And what we found is that you could cut about 80% of the vertical wires, and routing was still okay. Like the channel width you needed still wasn't changing much. If you went beyond that, if you cut 90%, well, that's 85 and 90%, now things were getting bad. Like you had to actually add a bunch of routing elsewhere to try to like make up for the fact that they've got this huge choke point. And it's interesting that if you do the numbers for Xilinx's 28 nanometer part, they cut 77% of the wires. So they're basically around here. Okay, so they're at a point where these experiments would say is still pretty good. The other thing that, that paper that I'm just referring to showed was that because the wires crossing the interposer are so expensive and scarce, you should do everything you can to avoid wasting them. So this is a case where you don't want to use direct drive, where you only have one drive point. You want to use tri-state buffers, be able to go left or right, and you want to use bigger muxes. So make these extra flexible, make them go both ways to try to get as much out of them as you can. But if you do that, in this range and below, it works pretty well. Okay. One ongoing question is, as we keep going to more advanced process nodes, the microbump scales some, but not as well as the transistors do or the other wires. So is it going to be possible to still get, 77, well, to get 20 or 25% of the wiring across? If you can, it's probably going to work really well. If you can't, it might get more problematic. And it is a bit harder to get the same fraction of wires across these interposers every generation. Yeah?
In this study that you did,
Yeah.
were the CAD tools changed to basically target one die more rather than the...
Yeah. So I actually decided there's no way I'm getting through it, so I cut the slide on that. But yeah, the paper talks about how the CAD tools were changed too. So the CAD tools were changed in multiple ways. The placement engine understood that crossing these boundaries was problematic, so it tried not to do it. And then it was also augmented with the partitioning engine. I told you partitioners work pretty well. So the placement was kind of started with 4 separate partitions. And then it was allowed to change them, but it understood that changing them had drawbacks. Does that make sense? And you're right. Without that, actually, the results are much worse. So you definitely, when you do something like this, you want to change the CAD tools. And when I've shown these results to Xilinx, and it's nice they line up with theirs because they have their own CAD tools. So if it didn't line up, they would probably say, we don't believe your CAD tools are any good. So it actually was kind of nice that they'd lined up. So, and it's always actually possible, right? You can get it, if you don't optimize this well, you can certainly get a different answer. So, okay, so Intel is also using interposers, but in a somewhat different way. So what they did in Stratix 10 is, okay, so Xilinx basically goes, we're going to make identical dice, and they are the FPGA fabric, and we connect them with these really beefy interposers. What Intel did is in Stratix 10, they still have a big FPGA die that does everything, and then they basically moved some of the high-speed I/O, particularly the transceivers. Transceivers are these serial I/Os that have clock data recovery and PLLs and so on. They're really fast, they're really complicated, they're really actually fairly big. They put those on separate little chips that they call chiplets, and then they used little interposers to connect them that they call, well, here they call them AIBs. Now sometimes they call them EMIB. So they're also using interposers, but kind of in a different way. They're doing sort of more heterogeneous integration. Xilinx is like, make me multiple things that are the same, wire them up with lots of wires in the interposer. Intel's saying we can optimize the fabrication technology for these transceivers and make a bunch of chiplets differently than the fabrication technology for the big FPGA, and then use interposers to connect them all together. So this is kind of a side-by-side comparison of what they look like. I already talked about this. This is what ultra-scale looks like. Well, Xilinx chips look like, basically. And it uses a TSMC technology that's called CoWoS. And Intel uses this EMIB technology, which is a little interposer, that's what that is, that just goes underneath part of the FPGA and part of these I/O transceivers and connects them together. And they're, yeah, different, and there's some interesting trade-offs. In theory, Intel could actually make a bigger system than Xilinx could, because Xilinx still needs, this interposer is actually one piece of silicon. And you can only make a piece of silicon about 800, maybe slightly more than 800 square millimeters, because that's the limit that the optical cameras can image to actually draw on it. So Xilinx has made some really big FPGAs, but they kind of can't go beyond that 800 square millimeter limit. In theory, Intel could go beyond that, because they can, their interposer just kind of goes underneath the edges, and they could put a whole bunch of them. But in practice, they haven't made, they've made big chips, but they're not really bigger than Xilinx. So it's not clear if that really matters. So anyway, but if you're interested, there are some detailed differences between them. One of my group's active research projects is with Intel, where their latest multi-chip integration technology actually lets them have transistors on multiple dice. So the interposers don't just have to be wires anymore. They can actually have logic and RAM and so on, and what can you do with that? So I think we're going to see more and more interesting heterogeneous integration like this. So that is it for interposers. Any questions or thoughts on that? Okay, so next topics, many topics today. So registered routing. So Stratix 10 is a really interesting FPGA architecture because it changed a whole bunch of stuff. And the motivation for their changes are that designs are getting to be more and more register rich. Okay, so they're pipelining deeper and deeper to go to higher clock frequencies. And part of the reason for the deep pipelining is that going across the chip, like just going from a register to another register, if it's going a significant distance, even that will limit your clock frequency, just stacking a few wires together, or maybe several wires together. So they'd like to be able to deeply pipeline, including with no LUTs in the middle. So that means you need a lot of registers. Also, they note in this paper that the delay to get in and out of a logic block, like you can pipeline using the registers in a logic block, but there's a delay to get into the logic block, a delay to get out. So if you're just trying to get from one part of the chip to another, you kind of take a delay hit every time you go in and out of the logic block, which means essentially you need more registers because you're not getting the full benefit of the pipelining. You're kind of wasting part of it with that delay to get in and out. So their idea is they said, well, what about just adding registers to the routing wires? That would get you a lot of registers. It means you wouldn't have to pay this penalty to get in and out of the logic block if you just wanted to insert pipelining. But in order to do it, we really need to make that low cost, because there are a lot of wires. Adding registers everywhere could be expensive. And you want the registers to be fast. If you can't make those registers fast, then this probably isn't a good idea. So the downsides are that these registers are going to be harder to use. So the registers in a logic block, because we have all that local routing and muxing, they're easier to get to. There's a delay to get to them, but they're kind of reachable from a lot of places. That's what all that local routing gives us. And these new registers right on wires, you know, you could use them on this wire, but some other wire is not going to really be able to steal it. The CAD flow is going to have to change. I was actually talking to one of my one of the engineers who used to work for me at Altera some years ago, who worked on Stratix 10, and he was in a pretty senior role. And his estimate was that the cost of Stratix 10 CAD plus architecture plus building it and everything for register routing was on the order of 1,000 person years, right? So he didn't have a lot of digits of precision on that, but he said, yes, this was like, this level of change was extremely time consuming to go and implement. And probably they didn't fully appreciate when they actually signed off on the chain on doing this, just how expensive it might be, right? There's an area overhead when you do this, because you are putting something into the routing wires, and there's a slight slowdown in the routing switch. So you're going to see they did this in a pretty clever way, but anything you do on a routing switch, adding any loading or circuitry is probably going to slow it down a little bit. In this paper, which is a pretty interesting paper to read if you haven't read it yet, is they don't talk much about this slowdown in the routing switch, but there will be some slowdown. And then another challenge they're going to have is how do they get the clock to these registers? So they know how to get clocks into the logic blocks and DSP blocks and so on. Nobody's ever had to send a clock to a routing wire before. And that could get really expensive because there are a lot of routing wires. Okay, so how do they do this? So the way they attack this is they want a cheap register. They want it fast. They don't want it to add much delay to the routing driver when they don't use it. So they don't build a register. They build a pulse latch. Okay, same trick that they used in Stratix 5, but kind of pushing it further, putting it right into the router. This is the circuitry. So they've got their usual routing mux, and there's the usual kind of weak pull-up. Okay, so that's what we've seen before. And this is a buffer, okay, so a pair of inverters. So all that stuff would be in the routing driver before. What they've added is these extra pull-ups and pull-downs and this extra latch. Okay, and I don't think I have time to go through it, but if you walk through this schematic, you can see that if they program well, these signals come from here, this N latch N, if they basically put a 1 in this SRAM cell, and it generates these two latch enable signals, basically this is on, and this is on, and the latch is turned off. Okay, so they can program an SRAM cell, and this is just a regular routing driver. It's a routing driver that will be a little slower because putting extra transistors in your pull-up and pull-down paths slow you down. But they say it's not much. If they program a 0 in here, then this is going to actually act as a pulse latch. Okay, and basically, I think I'm going to leave it as an exercise to you to walk through how do the signals work and convince yourself that this is indeed a pulse latch. But trust me, it is. So they have to add these transistors, and these transistors to put this pulse latch capability in. They argue that they only add 10 transistors and 8 of them are small, like the minimum size. And the original routing driver had 73 transistors and many of them were larger. So therefore, they only increase the area of they call it lab area. It's basically the tile increase. The logic block plus all the routing that comes along with it, they say gets 5% bigger. That doesn't include the clocking. Okay, so they haven't added in, well, how do I get the clock to this? Does that make sense? Because it does need a clock. This basically is a clock pulse. And they haven't shown, well, where does that clock pulse come from? So that's not included in this 5%. Does that make sense? Whoops. I'm going to take that as you're with me, okay? So anyway, I'd say this is I thought it was a very clever trick, right? So I like this trick. They didn't add much, and they get a fast, cheap register, because it's a pulse latch, behaves a lot like a register. Okay, then how do they get the clock to them? So, because this could get really expensive, right? If you have to have a whole routing network to get the clock to every routing wire, you go, wait a sec, that sounds kind of crazy. So what they do architecture studies in this paper where they show some of the trade-off space that they looked at. So Multera notation is they name multiplexers or routing multiplexers after what they drive. So they call what we've been calling a routing switch, like a switch block switch, they call a driver a DIM, a driver input mux. Okay, so we've just been calling it a routing switch. And the mux that is the input connection block that gets you to the input of a block they call a LIM, a lab input mux. Okay, so you've seen both those things, we just called them something different. Basically what they do is they have 6 clocks available. Those are in this part of a row. That's the last part of that ribbon spine network. These are the ribs they've muxed down to. And they basically built muxes that allow them to pick 2 of those, okay? And then every routing driver gets to pick. It gets 1 SRAM cell and 1 mux. It gets to pick between those 2, okay? So they got 6 clock sources. They pick 2 of those, and then every one of their routing driver gets a little bit of extra circuitry They get a 2-to-1 mux, they can pick one of those or the other one, okay? So that's smaller than giving every one of these routing drivers or DIMMs a 6-to-1 mux. So they're really trying to like squeeze it down as much as they can. And they do this, they group the driver muxes into groups of 50. So they basically, each group of 50 gets to choose 2 different clocks, and then every one of the routing drivers gets to pick between those 2. They also, inside the logic block, okay, so these limbs, what's going into the logic block, they just say they're all going to pick one of these 6. So they get a 6-to-1 mux, and they all have to use it. Okay, so every one of the muxes that go in here, of which there are like 52, has to share it. So they give a little bit less clocking flexibility to the input to the logic block than they do to the general routing switches. But they're pretty careful about how much they give both of them. Any idea why they give less clocking flexibility for these limbs, where they only get to pick 1 clock, whereas groups of 50 DIMMs get to pick from 2? What do you think? It's actually logical, but yeah. And that is true. So lots of these routing wires are not going to turn on their pulse latches. In fact, a minority of them are going to turn them on. So lots of them won't turn them on. So each routing wire can still choose not to use its pulse latch at all. So that's definitely true. Each limb can also choose, like each of these input muxes can also choose turn your pulse latch on or not. So you're definitely right. Don't assume that now every wire actually is registered. It's possible to register it, but most of them will be turned off in any given design. So, but there's still another reason of like, for the ones that do turn it on, they go all of the inputs to the logic block where they pick one of the clocks, they all got to use it. The DIMMs, they give a little more flexibility. They get to pick from pairs. And there's some logic to it. Why do you think they can get away with less flexibility on the clocking of these limbs? This might not be obvious, but so I guess inside of a logic block, the registers that are the registers that went in that logic block, they're related to each other. The logic that went in that logic block is related to each other because the CAD tools have been trying to group logic that talks to each other, and that generally means the registers, et cetera, in there are also using the same clock. So there's a reason these signals that are all trying to get into this logic block probably come from the same clock domain most of the time. Does that make sense? That's not so true of the DIMMs. The DIMMs are just signals driving by. Okay, these are the routing switches. So some of those might be signals that are, they came from not very far away and they're going not very far away, so they might use the same clock. But other ones might be, they were generated far away and they're just passing through. And in fact, those might be some of the ones we really need to pipeline because they're going to take multiple cycles to get across the clock. So there's less correlation in terms of what clock you're using on these DIMMs because some of them can be like long distance routes. And that's one of their use cases they want to optimize. Does that make sense? So they give a little more clocking flexibility there. Okay, a key barrier to this, pulse latches have not great hold time. And so they did this study seeing, it's actually always hard to know exactly how bad your hold time will be until you get a bunch of chips back and characterize it. You can spice it, but it's imperfect, right? Because your spice models might not be perfect. So they did this study of, depending on how bad the hold time is, what kind of frequency impact would that have when they're trying to use these pipeline registers? And basically, if hold time's really bad out here, it means they can't turn on, they turn on one pulse latch, they're not going to be able to turn another one on for several more wires. And that is going to hurt their frequency. And if they get out here, it gets pretty bad, right? Because they have to leave a lot of wires in between pulse latches, so they can't pipeline as deeply. They never say, what did they achieve when the chip came back, but basically it showed it's a key trade-off. They'd really like to have short hold times. So what do they overall get? They said that they increased area by 5% by putting in these pulse latches. Some more area, which they don't disclose for the clocking and control, because the pulse latch itself isn't everything. There's a little bit of slowdown because they put that extra circuitry in the routing driver for the pulse latch. They don't say what that is. So there's some costs that are not really just detailed. What they get is they get a lot of registers, like a huge number of registers, because every routing wire can, in theory, be a register. so they can retime logic very aggressively. They can pipeline very deeply. And then they show results in this paper that says that without redesigning circuits, they can get 45% higher speed on average. Now, some of that's process technology, some other architecture enhancements, but a lot of it is this ability to push the registers around. And they say if they redesign the circuits, so essentially go in and find what's limiting them and try to pipeline deeper, try to get rid of loops. We saw loops are a problem when you're pipelining. They can get up to 92% with some redesign. So you can't separate how much registered interconnect gets them, but 30% might be a reasonable guess. I only say might be because it's kind of my guess, but I don't know what's right. And yeah, they had to invest a lot in CAD tools. So to get maximum benefit of this, they really need to do retiming a lot to try to push the registers around, not just in the blocks now, but also into the routing. And they made tools to tell people, I'm being limited by this loop. You know, I couldn't retime, or I couldn't, you know, if you pipelined more and you got rid of this loop, it would help me. Since Stratix 10, Intel's had one more chip. Agilex is their 10 nanometer and 7 nanometer chip, and they backed off this a bit. So it probably says that the hold time problems were probably a little worse than they thought. They found that they couldn't turn on 2 pulse latches on consecutive wires. The hold time wouldn't permit it, which made them, and then the other thing that happened is the wiring resistance is going up, which meant that they have more short wires than they used to have, because long wires are somewhat harder to fabricate, which means that means the delay per wire is lower, which would mean that instead of having to skip every second pulse latch, maybe they have to skip skip 3 out of 4 or 5 out of 6 or something. So what they did is they changed to a smaller number of registers in the routing. So only a third of the wires, basically not the shortest wires, have registers, and so they put them on a smaller fraction of the wires, but they made them actual registers, which will have better hold time, but cost more area. So they decided fewer, but a bit more costly will be a better trade-off. Still a lot of registers, so they can still very deeply pipeline. And I think the benefit is basically hold time. I can't think of any other benefit. Like, pulse latches are small, they're fast, that's all really good, but their hold time is worse. And I guess this statement tells you that they were somewhat limited. And I mean, it still means they could turn on a lot of registers, but they had some constraints due to hold time of exactly where they could turn them on. They needed to leave a gap of a few wires after that. Well, at least another 1 wire without it, maybe 2. Does that make sense? And then they thought it would get worse with the increasing number of short wires they had, so they wanted to make hold time better.
Why did they not perhaps go with fewer pulse latches, just spread out more?
They could have built fewer pulse latches. You're right. I think my guess is that they wanted to make the hold time better, because they probably had, that was probably a challenge for them with pulse latches. And then once they decided that they weren't going to put them on all the wires, because they couldn't use them on all the wires in sequence anyway, that the cost of adding real registers was now amortized, so that they decided that the benefits of putting a real register in there and getting a better hold were a good trade-off given the reduced area hit. Does that make sense? That is my guess of what they're doing. Well, and they say some of this in the paper. Some of it they kind of give. I can't remember what parts they tell you and which parts you guess, but they tell you some of this in the paper. So I'll go through like a couple more slides, and then we'll knock off for today. Okay, so let's talk about what Versal did. So Versal is Xilinx's 10 nanometer and 7 nanometer chip, and it's an interesting divergence. Like, it's always interesting when different FPGA companies do different things. So Xilinx basically decided not to copy this idea. Like, when one vendor does something and the other one copies it, you kind of can say, well, it's probably a good idea, right? Or maybe they're just sheep. It's always possible, but usually it means well, it was probably a good idea. In this case, Xilinx explicitly decided not to put registers in their routing. What they did instead, so they already have registers on the output of their lookup tables, so did Intel. They added registers on the input to their lookup tables. And they're bypassable, right? So you don't have to use either of these registers. They did that, so they agree that designs are getting more register rich, so they put more registers in, but they think putting them on the routing wires is too much, so they didn't put them on the wires. Does this look useful? So what do you think? Like you already could register the output. Is registering the inputs useful as well? So you guys are saying yes? Is that just because you go, well, they spent a lot of money on it, they must have thought of this? Xilinx said they spent $1 billion developing Versal. I mean, it's not just on the registers. So yeah, you kind of hope they did some analysis, right? Otherwise, whoever put these in, if there was no analysis, that was a career decision perhaps. So the thing is that they don't look useful at first, right? You go, well, if I turn on the register here and I turn on the register here, that's just a lookup table. That's not much delay. You know, isn't most of my delay going to be in the interconnect then? Because it's going to be hard for me to get my critical path being just one lookup table. So it seems like this won't help that much. Maybe it helps a little. You have a little more freedom of where to put the register, but not that, you know, you don't, if you have a long interconnect route, right? This is what Intel was trying to solve. Being able to turn on a register in the interconnect kind of cuts that in half. Being able to turn on a register at the input to the LUT doesn't cut it in half. It just cuts off a little bit at the end, which is nowhere near as useful when you're pipelining. So it seems at first that this is maybe not super useful. Yeah?
You could have the combination path run through a LUT and then activate the registers.
Yeah, so you can have combinational paths that go through multiple LUTs. That's the classic combinational path too. But if that happens, it means you've got a register at the input and register at the output. So this one, already you could use the regular register. And this one, already you could use the regular register after this LUT too. I guess the one thing you do is, this was driven by a previous LUT, you could say, don't put it with the previous LUT, put it with this LUT. And okay, that would help you in that you got rid of a wire delay. So it could help a little bit, but you kind of go, it doesn't help this case that much. And it didn't help the case where we're going between two registers much either. Does that make sense? Or where you just got a whole bunch of wiring. So to make it more useful, they put programmable delays in. So they use their same trick of move the clock around. And this is, again, kind of clever. So the idea is they can't put this register in the interconnect, but they can move the clock around so that it kind of seems like it's in the interconnect from a timing perspective if you had one of these long wires. So they give this example in their paper. So they got a register here, here, here. So 3 registers. They've got some logic delay, and they've got some interconnect delay. Okay? And this is just, let's just implement it on their prior generation. And they say the interconnect, let's assume, is 1.5 nanoseconds. The delay in the logic block's 300. Then after this register, the interconnect's 1 nanoseconds, and the next logic block is 300. Okay, so your maximum delay is this. That's your longest path. Critical path is 1.8 nanoseconds. So they say, okay, well, if we put these new registers in on the inputs, we can move this flip-flop from the output of the CLB to the input. Okay, so we have that additional freedom, and that balances our paths a bit better. And now our longest path, if you add it up, is 1.6 nanoseconds. It's actually here. So it's a little better, but it's not a huge gain. Then they say, okay, well, part of this is about enabling deeper pipelining. So let's say the end user goes in, they change their design, and they basically use the input register and the output register and the input register on the next logic block too. So they've added 2 more stages of pipelining. But this is where it's not very balanced, right? They've added more pipelining, but really the long delay is here. And they didn't manage to cut that in half. So this is a little faster. They get 1.5 nanoseconds. Okay, so this was 1.8. Then they went to 1.6. Then they went to 1.5, which doesn't seem, you know, it's okay. But they put all these extra registers in. The designer redesigned with more pipelining, and they're only a little faster. But then they use their clock delays, which we already talked about how they did that in ultrascale, so it's the same circuitry basically, to delay the clock to this register. Delaying its clock is essentially like moving it into the interconnect from a timing perspective. Okay? So by doing that, they basically are able to do some time boring, and they get it down to 1 nanosecond. Does that make sense? So it's a clever way to, they go, we don't really want to physically put it in the interconnect, but if we can delay its clock from a timing perspective, it can behave as if it was in this interconnect. Does that make sense? Yeah, you have to actually look at it and think about it. So it doesn't really move into the interconnect. It's just basically they still have this data delay, but they've added on some extra clock delay, which essentially extends that cycle, right? That's what's really happening. It extends that cycle, which shortens this cycle. Now but from a timing perspective, you can also represent that as just like, it's as if your flip-flop was there from a timing perspective. I extended this cycle, just like I cut its delay, and I shortened this cycle, which is like I increased its delay. So they're just drawing it in a different way. That's really what they're doing, is they're extending one cycle and shortening the one after. This is like my last thing that I'll talk about today, but any pluses or minuses versus Stratix 10? So there are some. Don't worry, if you have no ideas, I'll talk about it, but if you want to get out of here, let's go into it. So it's less area. They only put these on the inputs to the logic block. That's fewer places than all throughout the routing. Probably less timing overhead. So they slow down the block inputs rather than slowing down every routing wire. You can cascade a whole bunch of routing wires together, so that you'd rather just slow down the inputs, which only kind of happens once after perhaps several routing wires. Another thing is that the flip-flops that Intel puts in their routing don't have clock enables or clears, etc. So you can't use them for everything. If you need a flip-flop that has a clock enable, etc., they'd have some CAD tricks to help sometimes, but they can't always use them. Xilinx just makes completely full-featured flip-flops, so they're easier to use. The downside is this allows deeper pipelining, but not nearly as deep as Stratix 10. So Xilinx is intentionally showing this case of what if I put one register from a timing perspective in the middle of my interconnect, because they can do that. If this was something going all the way across the chip and you wanted to put 6 registers in the interconnect, they can't do that. To do that, they have to go in and out of a bunch of logic blocks. So I guess they can do it, but they'll have to use up a bunch of registers in logic blocks. They can't just directly stick them in, so they don't show that case. So there's a case where Stratix 10 and Agilex, like they can do deeper pipelining. And yeah, this is clever that they use their clock skewing circuitry they already have to shift this register's timing constraints. Okay, and I'm not going to talk about this because we're out of time. But if you're interested, it's in the slides. It's basically a system-level interconnect that is now going into the latest FPGAs, where you don't have to connect everything with these 1-bit programmable wires. You can basically, let me show you the key takeaway one. That was I can't show you it even really fast, but basically putting a little internet on the chip, right? So hardened, prefabricated packet switched routers that you can use to do your kind of big system level communication between memory controllers and high level modules. And so the next slides kind of show why that's a good idea. And Xilinx and another company called Acronix, another FPGA company, have both put these hard networks on chips in their latest FPGAs. So I think they're here to stay. It's the next level of system level integration for FPGAs. So anyway, sorry for going over time. That's it for today. As I said, I'll post some links in case you want to see videos of the remaining bit of the lectures, and I'll do a Piazza poll. Good luck on your last assignments, and don't forget to do them.